community together with Mantas Karžinskas. So this year is particularly meaningful for all of us because we celebrate the year of quantum science and quantum technologies. And many of you know that during October, the Nobel Prize was also awarded for groundbreaking work in quantum technologies. So it brings finally quantum science into the palm of the hand, quantum mechanics in a macroscopic electrical circuit. And this year we also have published our national quantum agenda. Today we celebrate our first quantum hackathon. So this event, as you see, is powered by Quantum Lithuania. We are here in the host institution, FTMC, and our partners, Vilnius University, Nauvian, Integrated Optics, Vilnius Tech, Kaunas University of Technology, BSV Ventures, Coinvest Capital, Kinesis, Spacecraft, and Embassy of Republic of Lithuania to the Republic of Finland. We are thankful for their support. So, today's program will consist of 3 parts. There are inspiring keynote lectures. There will be a panel discussion and the pitches from the teams that have reached the grand finale. So it's my pleasure to introduce that we have 3 keynote speakers. It's Professor Philipp Walter, Professor of Experimental Quantum Physics at the University of Vienna, Quantum Optics, Quantum Nanophysics, Quantum Information Group, one of the pioneers of photonic quantum computing. Let's applause. Yes. And so we have here Jenny Hasso, Manager for Relations in Digital Technologies at VTT, Technical Research Center of Finland. Jenny, yes, hi. And Dr. Saulius Vaitiekėnas, Associate Professor at the Niels Bohr Institute, University of Copenhagen, the leader of Quantum Matter Laboratory. Hi. Okay, so we are honored to have you all here with us today. Thank you so much. To begin our program, I am pleased to invite the director of the Center for Physical Sciences and Technology, Professor Ramūnas Skaudžius, who is the head of our hosting institution and will formally open our event. So, please.
Hello to everybody. And it's a bit difficult, it's a bit quantum time to say hello for you because it's 11:25. I was invited and I checked double. It's real time to open the event. 11:25. Of course, it's a little bit more. You check. But anyway, I would say good morning. Let's start, as a morning still. And distinguished guests, partners, colleagues, and I would call friends in quantum field. It's a great honor, and excitement to welcome you here today at FTMC, the Center for Physical Sciences and Technology. And I would say it's a historic occasion. A historic occasion because we have the first time in the landscape of the Baltic states in the field of innovation, in the field of research, the first time we have quantum event organized hackathon in the Baltic states. And first of all, I would like to express my also gratitude to participants. To participants because they were the first one who respond to our call to be part of this event, and they spent many hours, many days, and even weeks to find new solutions that might revolutionize the fields in the healthcare, communication, finance, and of course, defense. And I'm very excited to wait for this pitch. And today we'll have just top 6 teams here, but I believe it will be a big experience for them as well. And today, already Marzena mentioned, we have invited speakers. So one more time, very thankful for you that you find time to come here across the whole Europe. And the speaks, I believe it will be very, very inspiring. Of course, I should mention also our esteemed jury members, and I would name it. So it's Professor Mantas Šimėnas, Dr. Tadas Paulauskas, Dr. Karolis Stašys, Professor Remigijus Polavičius, Andrius Milinavičius, and Victoria Trimbel. So applause for them. And I still remember the week, not the whole week, but 3 days in Switzerland, where we talked a lot with Andrius and Victoria about quantum technologies And today we're having this event here. So I'm very inspired, and this is just the beginning for new future events, I believe, here. And any event, any action actually begins with the idea. The idea is the time when people gathering together and have their own inspiration to do more, and sometimes even voluntary. So I really wish to thank to Quantum Lithuania, the association. It's really powered this event. And the members of it, it's Vilnius University, Kaunas Technology University, the name of the company Novian, and of course, FTMC. So welcome today here to this special event. So welcome to FTMC, welcome to Lithuania, welcome to the future of quantum technologies. Let's begin.
We will go to our first guest. So from Austria, one of the historical European leaders, especially when we talk about quantum optics, photonics, foundational quantum experiments. Vienna is legendary in this field. And it's my honor to introduce Professor Philipp Walter, once again, leading figure in photonic quantum technologies with a PhD from University of Vienna, postdoctoral work at Harvard University. He returned to Vienna to build his world-renowned research group, whose achievements include creating a photonic quantum computer capable of functioning in the space. Professor Walter's contributions have earned him prestigious awards from the Fresnel Prize to an RC Synergy Grant. He continues to advance the field as a fellow of American Physical Society and OSA. He is a founder of Cubo Technology. Please welcome Professor Philipp Walter, and his visit is sponsored by Integrated Optics. Thank you so much.
So thank you so much. It's an honor to be here. I've seen remarkable progress and things going on here in your country. So I think I hope that this really is a kickoff moment for you guys to become part of the quantum technology journey that we will face around the globe. And I see you have everything in your hand here to become a strong leader in the European landscape and the global landscape even, with your research, industry, and so on. But before I keep going to basically please you with how great you are, let me talk about the things I like to talk about, namely why quantum technology is. How can I switch to my slides? Yes. Okay. Here we go. So why is it so interesting to talk about quantum technology and why you should care about and what's so fascinating? Okay. So, as you'll be aware of, quantum physics started really 100 years ago with the famous physicist names you heard of: Bohr, Heisenberg, Dirac, who really allowed to explain how nature works. So they were able to explain how the atomic model looked like. They were able to identify basically properties, and they came up with this crazy theory where we learn things are quantized. No, there's certain energy levels. There's one electron, not a half one, and so on. We all learn this in school, and we learn how to basically deal with these kind of pictures. However, at the core of this theory, there's this probability concept. It means we learn in school that, for example, if you have the core and then the electron somewhere, here we always learn it's somewhere there. There's a probability to find it, for example, in this upper half, 50%. We don't know what it is exactly, but everything is always related to probabilities. Fair enough, that allows to deal nicely with the properties and actually open the field of modern science, when all chemistry, all pharmacy wouldn't be there without the knowledge of quantum mechanics, that we can explain the atomic model. This quantization, quantum physics basically in action. Also here, the Vienna is from the early days a leading figure with laser optics, a laser science, which is also a direct result of understanding atomic properties and therefore applying quantum science knowledge. Also, the semiconductor industry wouldn't exist in this way without, of course, the insights that we get from let's say, first generation of quantum physics. However, one of the founding fathers actually pointed something interestingly out, and I would like to read this to you guys. He says, we'll never experiment with just one electron or atom. In thought experiments, we sometimes assume that we do. This invariably entails ridiculous consequences. We are not experimenting with single particles any more than we can raise this ichthyosauria, that's this fish dinosaur, in the zoo. Who was that? There was nobody else than actually Erwin Schrödinger just a few years before he died. So even the founding fathers of quantum physics figured out that It's crazy to consider that you guys can play with single atoms, single photons, because if you could do so, it would be ridiculous what would happen. And actually nowadays we face the second revolution that we can exactly do what he was fascinated about. Nowadays we have in labs around the globe exactly this kind of capability that we can play with single ions, as an ion trap, single atoms in these optical lattices, single photons, that's what we do here in Vienna, or microwaves, single microwaves in superconducting circuits. All of those quantum systems, very different, we can play with. It's almost magic. And this magic there actually opens, besides the understanding of the Earth and the world, it opens up new technologies. And here I've picked out a few branches that end up to a multi-billion-dollar market in the future. We have quantum computing, where I come to a second what it means, but you have performances you cannot achieve otherwise. You have quantum communication, in particular being secure to a level that natural laws protect you. You can simulate material science, material properties way more efficiently, and you can build sensors that go beyond what classical sensors can do. You see very broad directions, and you can dig into literature, consultancy reports from McKinsey, Boston Consulting Groups, and so on, that talk about many hundred billions, up to $1 trillion in 2040, what the market value could be or will be of those things when they enter, when they lead to this paradigm shift in technology. Being a keynote here and coming from Vienna, I like to take a step back, okay? For those of you who are not familiar with quantum physics, namely, I would like to show you what's the magic, and where does the magic come from in our in the second quantum revolution, and why Schrödinger was so puzzled to say, guys, if you could play with single atoms, would see ridiculous things. What are those? So I would say for me the most prominent thing is the so-called quantum superposition, and linked to that randomness principle, where, let's take an example. I take a quantum system. I'm a photon guy, so I like photons. That's the smallest thing. They cannot be less than that. I take a single photon and send it from one side here on the left to the right. And on the right, it passes a beam splitter, which is basically a glass plate where 50% of light can be transmitted and reflected. Very commonly thing. You can buy those from the shelf. You use the laser light, that half of the light is reflected, half goes through. That's it. However, when you take a quantum particle, which cannot be split into one half, you enter quantum mechanical rules. Again, probability theory, which says, well, the particle goes simultaneously straight and is reflected. In the layman terms, it goes both ways simultaneously. That's not totally correct, because it means more like both probabilities coexist, but it has something that's not existing yet in classical world. So it really has some magic that both values exist at the same time. We do now put detectors here, then you will get a random answer that, for example, will be found there. So that's the randomness. And we cannot predict which detector will click. So that the magic things are superposition, two properties coexist. And if you look which is there, randomness kicks in and says, now we be, for example, at port 1. And then we stay there. Exactly this feature of being superimposed and then not being able to predict where it will be found is something Einstein was puzzled off. He said, the weakness of the theory, quantum mechanics, is that it leaves time and direction, in other words, the measurement process here, here in these words, time and direction of the elementary process, to pure randomness. He was super unhappy about that. It makes sense at that time. They had the mindset of theory is good when it can predict everything. And quantum mechanics intrinsically has features that cannot be predicted. And the other things that go beyond that with what's real and locality and so on, that will not be the topic of today. But it was amazing times that people realized there's something magic going on. And again, I bring this up to show you, you guys have magic nowadays really in the labs, and we can hopefully transfer this to a new technology level. So being not esoteric to say, actually, what we're talking about, because at the end I put a detector and we'll get a click. I cannot say what happened before that. There was really the argument that days it's esoteric to discuss what happens before you measure. It could be anything. It could make even dance the photons, yeah? So people said, wait, maybe we can do something. We can maybe make smart measurements to say it was superimposed. And nowadays we have the capability to do so and actually make a proof to you guys that this is really happening. So how do you do it? With optics, it's very elegant. You take, you extend the arms, that you add two mirrors on this side and that side, and then you combine them by another beam splitter, which is 50% transmittive and reflective. And now you put this guy here, that they're linked, and have an interesting result. So now in the case that, oops, I skipped out of the presentation. So now in the case that it was not disturbed and you have this superimposed situation here, then these probabilities interfere and result that only light comes out of this port. Okay, very nice. If something happens and nature would know where the particle is found by the detector, maybe that even air was density there, that basically whatever, some machine, or if you want to be spiritual, God would know where it is, then he would say, we destroy this effect. Particle, for example, is observed here, and then when it comes to this detector, it can go both directions, and you would see sometimes light coming out there where it shouldn't be. So in other words, we have now these methods to prove to you, yes, we had this magic before existing here. We have a different outcome at some parameter setting, then it was destroyed. And exactly this concept is nowadays used in a shifted way for enabling a new level of protection of data. Because now we can send quantum light prepared in such superposition states, and send it from one sender to receiver, from a sender to receiver, and if somebody listens to the photons, want to extract information, want to learn something, he must disturb these quantum superpositions, therefore it changes them, and at the end, a smart receiver would, by a similar method I've shown before, identify something has changed. And that's novel. That wasn't existing before, that we can now detect eavesdropping. There was no communication scheme so far that could tell you somebody was listening to my radio waves. This and a twist of that allows to establish now keys between these senders which are protected by natural law, allowing basically information theoretic, in other words, absolute security for communication channels, which is the field of quantum cryptography. And it's actually pretty old. It goes back to the 80s, where people had these crazy ideas you could use it, and nowadays it's pushed to the limit that people around the globe make this as a national initiative. There are plenty of startups that build such devices to protect this kind of communication channel. It's particularly interesting because quantum computers, unfortunately, can crack classical codes very efficiently. So the vaccine for quantum computer attacks is again quantum technology that you now use quantum light to build quantum infrastructures. So I show this picture here to show that nowadays we have these communication infrastructure initiatives around the globe, where also your country, Lithuania, is in part of that. So it tells you that nations are fear of missing out. So nations nowadays have to justify why they do not take care of their citizens by establishing infrastructure that allows to protect against the developments that are happening right now from either quantum computers or from other technologies that jeopardize bank transfers, public health data, national security data, and so on. And I show also here the satellites because the distance is limited by light being absorbed after some distance in fiber. You cannot boost it. So people think of communication via satellites to extend the distance, and therefore every country literally has one or the other way interest to establish quantum communication with satellites to make a global secure network. It's a big term of quantum internet, where when you Google that, you will find almost every country in the world having its own motivation and initiative to work on that. That's communication, but we have other things that work nicely with quantum technology. Very hyped these days is the so-called quantum computer, where the benefit of the computer comes from the fact that now with one single particle, as I've shown you before, we can now address two parameters, namely 0 and 1. That's different to classical computers because you have only one state. You send either a 0 or a 1 value, and you run them quickly after each other to see what comes out, but never simultaneously. It can't work. There's no classical computer where the input has both values with the same bit. You say either 0 or 1. That's different to quantum mechanics, where with the superposition principle, we prepare this very fragile 0 and 1 as coexistence in there. So just to give you an idea how powerful this is, well, if you have one quantum bit, you just have two values. If you have two quantum bits, you have already 4. And you see it goes exponentially because each one multiplies by a factor of 2. If you have 300 quantum bits, 300 bits is nothing, but 300 quantum bits gives you this number 2 to the power of 300, which is roughly 10 to 90. And the number is magic because it's bigger than all particles in the universe. Okay. So am I saying that right now, do we put the entire universe in 300 quantum bits? Not really, but I'm saying the huge amount of information such a system can process, okay, is amazing. It's really a paradigm shift in information processing. Of course, in reality, there are drawbacks. You have to put error corrections. You have to think of a smart way what to do with it. But it shows what kind of information is containing in just 300 dots, quantum dots. Okay, it's really something. So how we do it with light? So there are many groups work with different systems. I can talk about photons because that's close to my research. So how do we do it with photons? We actually, let's see if it works. So we send now these single photons not in bulky systems, but rather integrated optics, that we have a mode where light goes like a glass fiber, but now it's a chip. It goes in here, and it couples to the other one. It's properly aligned. There's a 50% chance to go this way and that way. And if I show you again at the end, if you do it properly, you superimpose at the end, and you have a quantum bit that occupies these two modes with one particle only. So now the question is, of course, wait a second. We learned we make superpositions, and then comes randomness. So when I now take a look at my computer, I have good random answers, and that's not what you want. So where do you get the benefit of having this massive parallelism, and yet you do useful things without seeing just out of this trillion answers, you get a random answer out. They say, I don't care about this one. The magic is the processing. So now you need a way to process that bad answers disappear and just good answers survive. And the answer to that is, we go back to what we learned in school. You use it basically as wave properties, that we use interference to suppress the bad one as destructive interference. You see, so what do you see here? In these terms, you have, for example, different interference here of a peak to a dip. They basically cancel because the top and the plus and minus become zero here. When you have basically two tops on each other, then you see they become enhanced in this new wave. So this wave here is the resulting wave of these two, gets much bigger. Basic optics, we learned this in school. And interference can or you throw a stone in the water. You see that there come new waves, which are some much higher and some disappear. So this interference also exists for the properties, the material itself of quantum mechanics. So we have these probabilities who interfere, who lead to the fact that if you have a quantum software, the challenge is it does something useful, that at the end the software gives you only one answer by interference, that when you send in, for example, light in here, they're also superimposed, they interfere, so they calculate something useful, and at the end of the output, ideally have only one left, or you see you have different output distributions because of interference. That's a quantum algorithm. It does, as I say, it manages that interference allows you to come to result much quicker, okay? And remarkably, the best, most efficient interference algorithm relies on quantum Fourier, so Fourier transformation for the experts is related to those features, is the Shor's algorithm, which allows to crack our current codes. So this one runs so efficiently because everything comes together for this code, for this software, that allows to be well done on the quantum computer, actually. So the fear of the classical security guys is this kind of capability that the quantum computer can crack this typical standard codes called RSA. However, there are other algorithms identified that work nicely. One is search, where you have a boost that cannot be done classically. We are able to mimic, to rebuild also atomic systems, basically by building it in the lab, which allows to study material sciences more efficiently than nowadays with classical simulations. When you look closer at chemistry or pharmacy directions, it takes years these days to simulate how molecules or medications should work. The reason is it's very hard to simulate these atoms with this exponentially big parameter space, and here people see a billion-dollar market to speed up developments of drugs, pharmacy, and so on by using quantum computers. And the last trend is where we also contribute in our group is machine learning, where quantum computers show interesting twists that for some tasks they seem to be faster, might be even lower power consuming, which is a very big hype these days when you be aware how much energy and resources are taken for these large language models, ChatGPT, in our systems. So moving to the computer that we build in our lab. So now I would like to show how a quantum computer for photons look like. Basically, you build here a single photon source. That's the challenging part. It's very hard for us to build light sources where just one photon comes out. You can easily build lasers, or not easily, but you need experts like here. You can turn on the light bulb, but these are the wrong lights. You want to have one photon only, and it's ridiculous how hard it is for us to get it. So nature fights with all its tricks that we have a big challenge to get these single photons. Nevertheless, there are ways to do it. So once you manage to get those single photons here from the sources, we let them dance on an integrated chip, so they come in here, and then we can tune what's going on, and we detect every end with very efficient detectors to see even single photons with almost 100% efficiency in our labs. And the lab looks like similar lab to around the globe. Big optics tables with lasers, cryostats for the particular sources, and you see we have basically all these typical square meter areas to run our quantum computers in the lab framework. If you want, you can also go to photonq.at, where you have online access, sometimes at least, to our hardware, and you can really make your own, get your own impressions what's going on there. In the big landscape, there's really a global race, a global effort in building quantum computers. It's done by academics up to industry. You see here really very different developments. So what you see, here's the time, the years. So right now we're here in the year 25. Here, basically, you see the size of the computer in terms of qubits, okay? And then you see there's very different architectures from ions, atoms. You don't need to read the details. It just should show you what kind of variety of it. Some people focus rather on still small qubit sizes, but here they focus on high quality to have low noise and even longer lifetimes. Others say we rather have many qubits, even though they're not that, they have noises and not that good quality steps. So in terms of quantum computers, there are two parameters: how many qubits you have and how many steps you can do. It's basically volume. People also call it sometimes volume. And you can choose where you want to like to be good in. Of course, you want to have both, but it's very hard. So people rather focus on different directions. The reason it's so diverse is because it's still an active field. We don't know yet the best architecture. And I think if you talk with me, a photon guy, I believe photons have a way to go, and the biggest company among those is still PsiQuantum, who has $1 billion investment to build those things. If I talk to my colleague in Innsbruck, they would say ions is the way to go. My colleague in ETH would say it's superconductors, which is good. It means there is no clear recipe, which means it's the right time to start the business. And I'm sure if there's so many people playing the game, there might be still a new one coming and saying, maybe why don't we do it that way? Nevertheless, it's happening everywhere. And also if you ask me why, because I have this question sometimes, why are academic groups still focusing on quantum computers to build when now people like Google or companies like Google, IBM, the big groups join them? There would be two answers. The first is they don't know that all these groups are strongly tied to academic groups. Google works with Santa Barbara, IBM with ETH. So everyone has his own academic group still in there because it's so many new things to learn. And the other argument is something nice to hear from a colleague is that companies are forced on product developments, engineering. Academics are elegant. We can think of new twists. We can think of crazy stuff. You can say we have this blue sky research freedom, and which is so important that every month new twists come from academic groups, what can be done with quantum computers, okay? And it goes hand in hand. Also, our group is focusing on what can be done, what else has nobody seen before as an application, can we modify something, and that makes it so beautiful. So in that respect, we have basically two legs in Vienna, that we still focus on the basics of quantum physics, and we investigate with our experiments. There's a tradition from my supervisor, Anton Zeilinger, that we like to investigate fundamental principles, yet we have to improve photonics technology that we can see them. And this led naturally to application that in the past we realized that photons are really a beautiful platform because in contrast to other systems, they're small, they're robust, you can handle them in ambient temperatures. We don't need vacuum chambers typically, we don't need cryostats, at least not necessarily. And we really could show that photons are very strong for a few applications. So of course, they're natural choice for sending secure communication, but we also could show new twists for digital payments, how to secure them. We could show quantum computers are also more secure. It's the only system so far that it can protect the data that the computer in the cloud gives you all the power, but yet it doesn't learn anything about your data. Just be aware that when you send encrypted data in the internet, Facebook, Tinder, bank account, at the end at the server, it's decrypted, it's plain text, because there's no way to process encrypted data. Well, there are some, but huge overhead. In the quantum world, if computers exist, it's possible. You can be protecting your data, and the computer will never learn what you're doing there, but it still works, okay? Which is a remarkable feature. So with some of our results, and they come almost to the end, we had a nice breakthrough in machine learning. We could, for example, show an artificial neuron that works with quantum light and allows also quantum boosts for neuromorphic networks. Here was got a cover page. And with that, we founded a company, Qubit Technology, that focuses on that, among other interests, to bring those things to the market. And if our motivation of boosting machine learning or boosting photonic computers, we realized that space missions are very interesting. So in fact, there are more than 1,000 satellites flying around at the moment with computers on board. Most of them look at the Earth and they want to digest quickly what they see, for example, to find a fire. So in Amazonas, they've all set, in Australia in particular, flying satellites around to find fires weeks quicker than human beings would see it, okay? And it makes a big difference to send firefighters there. Otherwise, it becomes, uncatchable anymore. So all of those have the challenge, the computers, there's no space, little energy, just solar panels, it's harsh conditions, and you want to be very efficient because the only communication to Earth should be the answer. I found the fire, it's here. They don't want to send a lot of raw data, which is then processed, because the communication satellites is very hard. It flies by and you have a few minutes to track it and then get the communication established. So you want a remote, strong computer. It's called edge computing. And we realized, well, quantum computers would be cool. And we said, luckily, we work with photons, which are suitable for space missions, because there is space-proof technology available for optics. And we took the challenge to build a small-scale quantum computer for so-called small CubeSat. It's roughly 10 kilograms, 3-liter volume. So we shrink the entire lab you've seen to such a thingy that survives the rocket launch. So we can throw it from the 5th floor, and it still works, a quantum computer. When you've been to a quantum lab, you know you stop breathing. When you go in and say, everything is aligned, and I see for an hour the results, and then you go out because everything must be aligned. That, when you remember the first slide, nobody's allowed to observe what's going on. When you be lousy and it shakes or misaligned, then nature would know, this arm is longer, it comes earlier, the superposition is gone. So you must be like a clock worker, very precise, or clockmaker, as they say in English, to be very precise to make those things. However, we did that, and we hope it's also opening directions for other remote computers, for drone satellites, and so on. So we are happy that we launched in June the first satellite. There's a picture of our launch in California. We are happy because it operates since then. Everything on board is working. You see here a picture of our satellite. It's a cartoon, but it's the picture of a real satellite. We have, very proud, we have here Lithuanian technology inside. We have a laser from Integrated Optics as a laser source for our designed payload. And we are very proud it's really made in Europe. So it's something where we'll be ahead of other continents. And now we still, please keep fingers crossed that it keeps going. We are still in an alignment process to get our things running in a proper way, but already we have succeeded. It works. Everything else now is basically a top-up of what I wanted to show. With that, I reached the end. I want to encourage you that here you have an amazing potential. It's amazing to see so many motivated and fascinating things going on. I'm very happy for being here. I'm very pleased and honored for this very nice hospitality that you showed to me. And if that, I really be the last slide and say, well, hopefully make the best out of these days. Use as a kick-off for your future quantum ecosystem here in Lithuania. Thank you.
In your opinion, what was the biggest technical challenge in adapting such a quantum computer for operation in space?
Everything. So we started from scratch. So you have to build something nobody knew how to build it, to be space-proof, to be shock-proof, to operate. So it was an amazing team. So I must say, I've never seen in my career such a dedication that money couldn't buy it. People have seen a chance to be the first in the world, also in this quantum year, and they worked literally day and night shifts with a passion, and it was really like, you build something, if it doesn't work, throw it away, start again. There was very pragmatism, okay? And you see what people can achieve when the motivation is there. From intrinsic, from themselves, not I say you must, that doesn't work. it really was beautiful.
And if we talk about practical quantum optical communication, how do you think which approach is currently more promising, discrete variable or continuous variable protocols?
I think very good question. So you can encode differently light in discrete states or continuous in squeezed light. For short distance, I think squeeze in continuous variables is the best way because you have much higher data rates. Okay. If you go for long distance, you probably have to switch to discrete variables. Okay. So it depends on your application. You need both. It's my impression.
I see. Do we have any questions from the audience? Okay, Director of Quantum Lithuania.
Thank you for a very interesting presentation. I would like to ask you, please compare, how to say, perspectivity of the different approaches for quantum computers, superconductors, photonic quantum computer, called atoms. What would be their advantages and disadvantages, in your opinion?
It's very equal in my eyes. So every system has a severe challenge, as we say it, okay? And some developments are secret because companies are so much advanced, they say we don't want to give insights into how far we are. For me, it's more like a personal flavor where you feel more comfortable to dig into your problem. So I like photons, and I believe photons have a standing there. Companies believe in superconductors, which has had amazing progress. But all of those have challenges. We say there's still many things in the future need to be solved to really make this next big jump ahead. I don't want to favorite one or the other system. It really depends on the people behind it. People make the difference. If you have amazing people with one architecture, they could rock, okay? So that makes a difference. So I would not go by hardware driven, rather by who is the right guy or the right team, and then choose your system.
I would like to ask you one more question.
The last one.
What are the biggest present challenges related with photonic quantum computer?
Mainly it's the generation of photons. So it's hard to get single photons. And with that, since it's hard to get, you have to optimize the losses. So if you fight with producing them, you have to be very good in not losing them on the way to the end. It's a photon source. So if somebody develops here a bright photon source where I push a button, it comes out a single photon, become millionaire right away. Okay, so please work on that, yeah. And we buy it. Yeah,
Since we are strict on time because taxi is already waiting for Philip.
I'm sorry, I have to run back to Vienna for this
So
afternoon.
we have a special gift from Center for Physical Sciences and Technology. Mantas will give just as a memory for this event. Let's
thank you so much.
applause. Thank you so much.
Thank you. It's a true pleasure. Thank you so much for inviting me. I really enjoyed it a lot. I know it was a short time, but it's very, very impressive what you try to build up here, and I wish you all the best. And I see good reason everything will work out.
Thank you, Philip. Have a nice trip
Thank
to
you.
Austria. Thank you so much. Okay, so we are moving forward. I am delighted to introduce our next speaker, who represents a country that has a very robust and fast-growing quantum ecosystem. It's strong in cryogenics, in superconducting qubits, microelectronics, and national strategy. So we already know the answer, it's Finland. So quantum expertise in Finland is the result of decades of dedicated research and innovation, placing the country at forefront of quantum revolution in Europe. And it's my pleasure to introduce you Jenny Hasso, Manager of Digital Technologies at VTT Technical Research Center of Finland. Jenny works across quantum technologies, microelectronics, new space, connectivity, and served as the Secretary of Finland's Quantum Technology Strategy, which was released this spring. She also authored the recent national report, Critical Digital Technologies of Finland, helping shape strategic recommendations for Europe's innovation ecosystem. And today she will speak about Finland's leading role in Europe's technology landscape in quantum. So please welcome Jenny Hasso.
Thank you. It's my second time in Vilnius. First time I was here, I was a student. I was staying in a tent in the summer, and it was really hot. So it has been leveling up in my life. I'm staying in a hotel now, so it's much pleasant. I have a presentation as well. Where? Now someone else's. Oh, it's there. No. Great. So, good morning, everyone. I'm from VTT, and VTT is non-profit, state-owned, independent research organization. We were founded in 1942 in the middle of the war. We are the major international player, ranked 15th among the over 21,000 recipients of EU research funding. We get our funds from the market, so we do business, and then we get funds in the EU as well, and a little bit as the Finnish state. But we are a company. Even though we are fully state-owned, we are a company. Sustainable growth and research and development is the heart of what we do at the VTT. We are a visionary partner for business and society, and we bring together people, business, science, and technologies. There are almost already 2,400 people working for us and more than 1,000 customers. And where we do our business, this is the pictures I like to show quite a lot. We are in the Valley of Death. I think many of you know this Valley of Death situation where you can end up with. So we are filling that gap. We are trying to help innovation emerge when appliance research works with industry to translate the new knowledge and understanding produced by basic research into practice. And who we work with. There are more than 60 spin-offs that we have originated from VTT. One of them we have already heard today. One of the spin-offs from VTT and University of Aalto is IQM. One of them is Bluefors. So we are in the heart of making new business as well. And we hope that, that the things that are studied in VTT would end up to be a business. And the partners that we do business within, some of them are listed here. Most of our partnership are, well, you know, when you make business, you don't always tell about it out loud, but these are our partners that we have open partnership with. Yeah, that was enough about VTT, I think so too. Let's speak about Quantum. Like said in the beginning of this morning, this is the year of a Quantum, and we have seen many beautiful things happening this year, and this event is one of them. So I really want to thank you holding it here, because yesterday I visited the Minister of Economic and Innovations of Lithuania, and I said that the Nordic and the Baltics could be some kind of a quantum bell when we rethink what we do and do more together. Today, this year, we published our first national quantum strategy in Finland. There was a vision, and then we make a step how to reach that vision. I worked as a secretary of this group, and I have learned that there is not still yet a strategy in quantum in here, but that there might be someday. So I will speak a little bit about our quantum, national quantum strategy. Then I move what the EU quantum strategy, what we want out of it. And then I try to take all together and make some kind of a conclusion what we should do more together. At the moment, the turnover of quantum sector in Finland is increasing indeed. There are lots of investments. Many of you might have read only this fall about the investments in IQM only itself. There are more than 500 jobs in industry, but we are seeking much more growth in future. Our key success factors include strengthening competence, flexible study paths for quantum experts, a competitive R&D environment, and world-class research infrastructures. Yes, we have set ambitious targets for growth. Well, for example, one goal of the strategy is to have 1,000 logical quantum computer in Finland. One may think, ooh, oh my God, that's too much, but we are actually thinking that we can do it. We put some points that we need to make if we wanna make this actually happen and work. Quantum Competence Center, it's quite self-relevant, and we do actually have it already at Institute Q. Some of you might have heard it or might have worked it before. We have world-class computing infrastructures. I will go to there shortly, but we want to improve it as well. A competitive infrastructure to support the development of quantum hardware and components. Yeah, I was in a committee meeting in our national parliament earlier this week, and I think this is the major questions that is asked everywhere where we go and tell about our work. It doesn't in national level or in EU level. What does it mean and how can we scale up what we are doing? How we will do it? I will tell it a little bit later as well. And then the fifth, long-term quantum R&D program. I think this is quite important in every national level if you are if you have made a decision to invest in quantum. You do need to have an R&D program. That's not only looking for the, let's say, to 2 years, but to 10 years, to 20 years, what to do and how to do it. We have been studying quantum in Finland and at VTT for 6 years. So, and even though this was our first national quantum strategy, there have been many investments by the government to quantum for 6 years already. So it was something that we just decided to do today and then started to build from nothing, from scratch. And this is how the Finnish quantum technology ecosystem looks like. You can see maybe some familiar names from there. There are RTOs like CSC, where is the supercomputer LUMI hosted at Kajaani. VTT. VTT is located, well, everywhere in Finland, but in major Helsinki area, Oulu, Tampere, Turku, and northern Finland as well. Companies, it's so small that no one can see, but we have tried to enlist companies that are even in our service or using the service of quantum. Universities, many familiar names to you as well, from Aalto University to the University of Tampere, University of Turku. There was, I'm sad that the last professor already left because I sent a memo to the Photonics of Finland that there is a keen speaker on photonics, and Photonics of Finland is a key player in our infrastructure as well, and they are always happy to hear that someone is speaking happily on photonics. Research funding comes from EU and Research Council of Finland, that is under the Minister of Education. Innovation funding from Business Finland, Finnvera, and TESI that are under the Minister of Economic Affairs, and EU and private sectors. Then we have quantum computers at VTT and a supercomputer at Kajaani. FIC is a National Competence Center of Chips under the CHIP Act. And we have infrastructures, Otanano, Micronova, where are the low temperature laboratory and nanocryobrase center. And we are building a new one, which I will come next. The strengths that we have in the quantum ecosystem, that yes, we have had from the 60s, very world-class groups building up quantum ecosystem. Like told you before, we have several, I would say, even world leaders in Bluefors and IQM as in well, that has come from startups are growing. We have quite a strong semiconductors and photonics industry supporting quantum technology growth. Then we are with applied research and state-of-the-art joint infrastructure and by RTOs, LUMI, supercomputer, and clean room test environment centers. And our working culture and public funding promote collaboration and open innovation between all ecosystem players. And all of this is coordinated by National Quantum Institute, Institute Q. if there is a one thing that I would like you to remember from my presentation today is state. What you guys were doing in the spring of 2020? Anyone? Remember that time? Yes, isolating, indeed. In spring of 2020, the Finnish state decided to buy a quantum computer. In the spring, April 2020. They gave money to VTT, and VTT opened an open application, open competition to anyone to participate. And the winner was IQM, a Finnish startup who has not yet by then built quantum computer. But via this process, they built first 5-qubit computers, then 20-qubit computers, and then 50-qubit quantum superconducting computers. And during that process, more than 250 scientists learn how to do it. And end of the process, IQM can say, yes, we have built a quantum computer, and VTT can say, yes, we know how to use it, and we have been building the computer with IQM. And even better, more startups came out of this process because people, while they were learning to do it, they were like, hey, I could do something with quantum myself. So everybody is winner. So now when we open a new competition for 300-qubit computer, we did it in the same way, in a public procurement and open application. This is something that we have been quite worldly towards EU, while they are doing their quantum strategy first and now Quantum Act. We would like to see that if the EU is going to buy quantum computers somewhere, wherever in EU, they would do it more like this, because this is really growing the quantum ecosystem. We have seen the benefits in Finland, and we are actually very, very pleased what have come out of it. Not only that we do have the computers, but the growth of the ecosystem, the growth of the scientists, the growth of the IP and learning. So if this is something that I would like you to remember, because when we look back 6 years ago, quantum in Finland looked very differently than it looked right now. And this is the one key reasons behind of it. Okay, let's go back to the VTT. I cannot lie, I love VTT, so I love to speak it as well. We have quite a lot of quantum technology at VTT. We have in-house infra, of course, and technology development for scaling up for quantum computers. We have 50-qubit computer. I'm not a physicist, but I will show you soon a picture of a computer that physicists will understand so much better than I will never do. So hold on your hats. What else? We are quite keen on microelectronics as well. We are hosting a quantum pilot line, and we are part of 4 other pilot lines under the CHIP Act. We have the largest clean room in all of Nordic countries, and several satellites in the space with VTT's technology inside. I was actually thinking to taking one of the mock satellite here with me, but I learned yesterday that almost all the people in Lithuania have already seen it. So if you want to see it, please come to Finland. I will show it to you. We had quite large IPR portfolio at VTT, and we are very active player in the Finnish and European research programs. And here is all of you quantum enthusiasts about our 50-qubit quantum computers. It was launched earlier this year in March, and it's now open to research, scientists, students, and companies as well to use. It is connected to the LUMI supercomputer, making it one of the world leaders in this hybrid mode of computers together with quantum and LUMI. And it's funded by the Ministry of Economic Affairs and Employment in Finland. And then I have a few words about the EU and why we are very active there as well. We are now coordinating the European Quantum Pilot Line Supreme in Finland, and there are the other countries that are doing it with us. And then we are joined with 4 other pilot lines at the same time. In Finland, we are member of 5 different pilot lines. One of the pilot lines, the memberships is from under the University of Tampere. And we are even looking for further bigger steps to take in the future. So we are indeed building a new fabrication to an RD hub for microelectronics and quantum technology in Espoo, nearby, next to Helsinki. This building is called Kvanttinova. And usually when I say Kvanttinova, everybody's like, oh, it's only quantum. No, it's microelectronics as well. So this is quite interesting. It will be the biggest R&D hub ever made in Finland. And we are going to placement under the CHIP Act of the pilot lines in this new building. And the private investment estimated to be 500 million euros. This is a co-owned, how you say, organization of Aalto University, VTT, and City of Espoo. It will be a unique co-development environment, and where VTT is operating the pilot lines and companies' own facilities can be used. It means that we have, like this open application where you can rent a pilot line, let's say for a week or 2 weeks for the needs of the company. And we will start building it early next year. Then I promised few words about the upcoming European Quantum Act. As a member of European Union, as you guys are, we are very keen to know what is going to happen next. In the coming up Quantum Act will be the first official movement of Europe on a quantum. We are seeing that Europe must have top-tier quantum computers considering different quantum modalities, just like the first speaker was saying. In Finland, we are very keen on superconducting computers, but we do know that we need to have all of them, and we need to raise all of them up because, we don't know who is going to be a winner, if you may say so. And they all must be integrated with the Euro AHP high-performance computing and IA hybrid computing environments. The European needs to have quite a strong role in global leadership. So, and that means that we have very focused aim while we are doing it. And that's what we have learned in Finland, and that I would like to say here, you guys here as well. So it doesn't matter if we are a national and EU level, whatever we do, let's do it in a way that it strengthens our own ecosystem while spending money on it. In the summary, VTT, well, it's not far away. It took me 1 hour and 40 minutes to fly here. It's less than I drive home from Helsinki to my family home. So please welcome. We are not far away. We are one of the innovation leaders in quantum technologies in Europe, and our specialized microelectronics and innovation multiphysics materials discovery. While I was coming here, I was thinking that what should I tell you about and Finland and potential and what you guys have here. And I would say quite a lot. We have the same problems, lack of students. We need talent from abroad. We need to go across our borders to look people, to do the quantum revolution. So we need each other. No matter what the steps that we are taking, no matter we are north of Europe or east of Europe, we need each other. So thank you very much for having me here. And I think it's very brilliant that you are having this quantum boost. And I don't know so much about the education system here. But I visited recently in Japan, and I give a lecture there about different quantum modalities, and I visited this kind of museum for children about quantum. So that's a tip to take. Thank you.
Thank you. Let's thank for Jenny. Okay, so do we have any questions from the audience? Okay, Sharonas and Peter was the second one.
Presentation, I would like you regarding the, how to say, quantum gap with clean rooms with pilot line you mentioned. Do I correctly understood that there is some kind of the common pipeline and there are spaces with equipment installed by the companies? Additional equipment installed by the companies in some kind of their own rented rooms in that clean room.
Yes, yes, they are shared and their own as well. So they're investing their own investments in the same. Yeah, yeah. But this is definitely something that will build ecosystem. You know, when you meet people in lunch cafeteria, you might get the best ideas. When you are in this shared spaces with different organizations, RTOs, universities, companies, that's the ecosystem working.
Thank you, Šarūnas Miškinis. Vita Markevičiūtė.
Well, I'm Vita, and I'm a Science Innovation Advisor for the Ministry of Economy and Innovation and at the Research Council. And actually, I just got back from EQTC in Copenhagen, and I spoke to your colleagues. Actually, I spoke to Institute Q. We also spoke to Danish quantum community and Estonian and Latvian quantum communities, and we spoke exactly that we need to form a joint ecosystem. And actually, we even spoke to European Commission that we want to form a joint position to the draft Quantum Act, and we asked for some time, for moving the deadline. So we didn't speak to VTT, but we spoke to Institute Q, and they promised to tell this to you.
Okay, great.
But I'm telling this now that it is really, you have our full support, and we are really interested, all the Baltic states and Lithuania, we're interested to forming this joint ecosystem.
Yeah. What did they say about moving the deadline?
They said, they told us some tricks, so we have about 1 month.
Okay, some tricks.
We're planning to meet next week, actually.
Me too.
Online.
I'm going to Brussels. So let's call after that.
Yes. So
This is ecosystem working in real life.
Exactly. So I'm talking for the ecosystem, actually.
Yeah, great.
Thank you so much.
Thank you.
So we see how networking works nicely. Jenny, you mentioned, Finland has positioned itself among European leaders. How do you think what is needed for Europe to become a global quantum superpower as China, as USA? Do we have the potential here?
Yes, of course we have a potential. Why else would we here today? One thing is that research is the key element here. So what you guys are doing now is very important. China is beating all of the Western world when it comes to IP, new research, students. They're investing heavily on that subject. So we need to focus that as well. I attended a Quantum Development Group meeting in Japan a little more than a month ago, and this was one of the major things that we discussed. It doesn't matter if you have the best quantum computers in the continent, you need to have end users. You need to think how the end users will gain from these, that we are having this infrastructure here. The computer itself is not the key here. It's the computer is, it's a key, but the computer itself is not the answer. It's the tool towards the answer. And then we have software users and think with the end users what we would like to have in this continent with quantum.
Yeah, I see. So let's thank for the speaker once again with a round of applause. Okay. We have also a special gift for our keynote. Jenny, yes, from the center, we're giving you the gift. And here, as you know, country of rain. So umbrella, because Lithuania, it's country of rain. So with great pleasure, I now invite our fellow Lithuanian, Saulius Vaitiekėnas, researcher whose contributions to quantum technologies have been truly outstanding. He's associate professor at Niels Bohr Institute, University of Copenhagen, leader of Quantum Matter Lab. His work explores how superconductivity, magnetism, semiconductors can be combined to create a new quantum materials and devices. He has contributed to several pioneering experiments in hybrid nanostructures and quantum circuits. Before taking his current role, Vaitiekėnas served as assistant professor at the Niels Bohr Institute, was a visiting scholar at Harvard University, worked as senior researcher at Microsoft. He earned his PhD in physics from University of Copenhagen and holds master's degree from Free University Berlin. So let's welcome Saulius Vaitiekėnas.
Thank you very much for the introduction. It's my pleasure to be here. It's always great to come back to Lithuania, where I'm come from. The last time I was here at FTMC, I think was some 6 years ago or something like that, where I visited as a student. And now I'm coming to talk about my research that I do together with my group at the University of Copenhagen. And as a dessert for the keynote talks, I'll go out with a little bit of a physics bank, and I hope you can bear with me. I'll try to keep it as least technical as possible. So I'll talk about less about quantum computers, but more about other side of quantum, namely the quantum phases and more quantum physics fundamental aspects of it. At least in the research field that I'm working with, you can think of moving forward along the development along two axes. Namely, you can think of it as doing research along classical to quantum direction, or you can also think from going from simple to more complex. And well, it would probably be boring to do just one of them. So we are striving to go along the diagonal where the unknowns lie. And my claim is that one of the directions that one can take is to use Josephson junction arrays that could help answer some of the questions along the way. So what are those Josephson junction arrays? And for that, I would like to introduce you, give a crash course to superconductivity for 1 minute. This is to be contrasted with normal conductors, normal metals such as, let's say, copper in your wires or gold that have electrons zooming around. So that's the red ball zooming around the nuclei in the material. And they don't, as you cool them down, first the nuclei cool down, the vibrations slow down, but then the resistance persists, and you can still do a lot of cool things with them. But there's a different type of materials, namely superconductors, and surprisingly, there's quite a few of them, where below a certain critical temperature, the electrons tend to pair up, and this has profound consequences to the material properties. One of them being that the resistance of the material drops to 0. This allows it to pass currents without any dissipation, meaning there's no heating involved in there anymore. And so if one could push this critical temperature out to room temperatures, that would revolutionize energy, infrastructure, and so on. We still work at very low temperatures and do research with that, but another consequence of electrons pairing up like this in the superconductors is that they screen out the magnetic fields from their interior, and these are the two hallmarks of the superconductivity. Now, if you take two superconductors and connect them via a weak link or an insulator, remarkably, you can still pass supercurrents across them. So there's still no dissipation, no heating. You can start making cool things with it. In particular, the superconductors are described by a microscopic wave function, which has an amplitude and a phase. And if you have a phase difference between these two superconductors, you can start having these dissipation and supercurrents running through it, or if there is a variation in these phases, you get a voltage drop across it. It's not, the details are not so important, but I just wanted to point out that all of these predictions were done more than half a century ago, which then deserved a Nobel Prize for Josephson, the guy who discovered these phenomena. The microscopic wave function that describes these superconductors has profound consequences. These junctions, in principle, are quite a bit more complicated than just sketched out here. And then these complicated nature of these junctions was studied in the 80s by the Nobel laureates of this year. And so that formed the core of these experiments. This is not to say that there's no activity involving Joseon junctions. There is quite a bit of activity going on. This is from now 2 years ago, but people are looking at all sorts of different Joseon junctions. In this case, it's an STM. New phenomena are arising, such as Joseon diode, which could be used in superconducting electronics that pass supercurrent one way but not the other. There's also still a lot of fundamental research going on in Joseon junctions. I don't want to spend too much time on it, but just wanted to give you a flavor of the directions that can still be taken on these days. And not only experiments, there are also new ideas coming out involving Joseon junctions and relying on them. Namely, if you arrange a bunch of Joseon junctions together, if you can connect them, you form Joseon junction arrays. And under certain conditions, if you phase bias them correctly and pass currents, specifically, you can form new types of matter, namely the topological matter, which has similarities with celebrated topological quantum Hall effect, with edge currents running around it. And some companies, for instance, like Microsoft, is using these topological properties of similar materials to try and do some quantum computing with it. In addition to that, you can build all sorts of complicated devices from these Joseon junctions, which can then enable you to do quantum simulations of exotic quantum matter, which has, from my perspective, a lot of fundamental interest, but then potentially also in the future some applications. A little bit more background to the Joseon junctions. Now these are the islands, Joseon junction arrays. These are the islands that are connected together through the tunneling barriers, and they then form an array. Each of the island or the connection between the two is characterized by the Joseon energy. But in addition to that, because they're separated by tunneling barriers, they also have some mutual cross capacitance between each other, and that sets another energy scale, namely the charging energy, which you can think of. If you want to put charge carriers on the island, you have to pay energy because of the Coulombic electrostatic repulsion. And now the consequence of the competition between these two energy scales is that the charging energy sets the number of charge carriers on the island, whereas the Joseon energy sets the phases of the islands. And if these two energy scales become comparable, you can have uncertainty between the number of particles and the phases between the islands, which is very similar to celebrated Heisenberg's uncertainty principle of the space and momentum. So basically, you cannot be certain about the phase differences and the number of the particles at the same time, and then this makes these Joseon junction arrays a quantum object. And because of that, you can use these Joseon junction arrays to study quantum phase transitions as a function of temperature, magnetic field, disorder, and all other sorts of tuning parameters. In my laboratory, we work with a very special type of material combination, namely hybrid semiconductor, superconductor material stacks, where the electrons in the semiconductor are confined in a quantum well. In this particular case, it's an indium arsenide. And so that's the blue one here is the potential barriers, and then red is the wave function of electrons residing inside of this quantum well. And this quantum well is proximatized by a superconducting aluminum, which is grown epitaxially, meaning that atoms are matched on the atomic scale with each other, and that is a crystalline quality interface between hybrid materials that enables a lot of cool new experiments. And the materials that we work with is both from collaborators, but also grown in-house by in my team. And then for the experts in the audience, the peak mobility that is the characteristic quantity that characterizes these materials is around 20,000 centimeters per volt second, but that's a little bit more of a technical detail. Now, we take these materials and fabricate devices in the house. Here, the blue is the leftover superconductor sitting on top of indium arsenide TUDEG, or the semiconductor. And the typical length scale that then we can achieve in the lab is around 100 nanometers or so. And to give you a little bit of a perspective, here is a zoomed in cross-section of a human hair, which is, maybe it's a little bit exaggerated by me, but it's on the order of 100 micrometers. And so now if you look at the ratio between them, you could fit on the order of 1,000 Josephson junctions on the cross-section of the hair. That's the scales that we are talking about. And just put it in the perspective, if you look at the diameter of the Earth and compare it with the diameter of our sun, that's the ratio is around 100. So the ratio between these two is smaller than the ratio of our devices that we can fit on an average human hair. So we fabricate these devices on chips, similar to any other chips in quantum field. And that's, each of the devices now has a slightly different color. Interestingly, I didn't false color it. It just came out like that through the microscope. And once we are done fabricating these chips, we want to connect them out, and then we bond them to these chip carriers, also sometimes called daughter boards, which we then place in the daughter board carriers, which are connected through a bunch of cables that then allow us to talk to the devices that we just fabricated, which are then placed at the bottom of a dilution refrigerator. This is a picture, maybe less neat version of a picture that you might have seen in announcements from the superconducting quantum processors. And here's my student for the scale. So it's not too tiny. It's not a size of a desktop just yet. But then once we place these chips at the bottom of the dilution refrigerator, we cover it up, pump it out, because we don't want any air in there. We cool it down to tens of millikelvins, which is 1,000 or an order of 1,000 less than environment right here. And then use a lot of equipment to talk to these devices and get information out of them and study their behavior. Just to give you a little bit of an example, what we are doing, this is a scanning electron micrograph top view of our device, and actually it's a very big zoom in showing 9 superconducting islands, which are then scaled out to 100 or so Josephson junctions. And they are then connected through the semiconductor to each other. And the difference between the Josephson junctions that are being used in modern quantum processors is that in our case, we are using semiconductors which can be tuned through field effect, just like all the processors in our modern technology, powering also this screen, etc. But just by applying electrical fields through voltages, we can tune the semiconducting properties and shuttle the electrons in and out, meaning we can either keep it on, or if we apply voltage, we can close the current off. And this allows us to tune the coupling between the superconducting islands. So we have one gate electrode. This is the frame gate that you can see in gold here. We call it frame gate because it frames the superconducting islands. And if we apply that gate voltage, we effectively can decouple the superconducting islands from each other. That's one of the applications that you can do. The other is the global top gate, which is not seen in this picture because that would cover everything and you wouldn't see anything anymore. But this can be seen as this big slab here sitting on top of the whole device, which then decouples the islands from the surrounding TUDEC and the frame, and then making the sample effectively non-superconducting. It's a little bit of a technical detail. But the thing that these 2 gate electrodes through field effect allows us to do is to study the resistivity of our Josephson junction arrays as a function of these 2 tuning knobs that we can tune in situ while the sample is sitting in the fridge, and we don't have to take it out and put it in again, take it out and put it in again. We just crank it at deliberate resolution and get phase diagrams like this. So here, when the gates are not energized, the resistivity is quite low, and then basically it's the blue part of the phase diagram. If we apply one of the gate voltages, we can either go to very high resistivities indicated here by the yellow line, or so basically it becomes dissipative, and then there is also an intermediate phase between both blue and yellow. So now we can characterize these transitions between these different regions, and if you tune the gate voltage here and look at the temperature dependence of it, you can see that there is a crossing point On the less negative side of that crossing point of this gate voltage, we see that as we tune the temperature, the resistivity decreases, and that's consistent with superconductivity, whereas on the other side, the resistivity increases. And so as we cool the material down and our sample down, it becomes more and more resistive, indicative of the insulating behavior. And similarly, if you look at the phase transition on this side, we also see a superconducting behavior on one side, and on the other side, it's somewhat similar to the insulating behavior, but it doesn't explode as much, and so we characterize these different phases in this diagram as superconductor, insulator, and metal. And this is all, again, the new thing about this capability is that it's all tuned in situ through gate voltages, and this allows us to state that our Josephson junction arrays are prototypical systems to study quantum phenomena such as quantum phase transitions between different types of matter. We can study quantum criticality, quantum interference, and quantum corrections. All right, a little bit of physics, but I'm pretty much done now. I wanted to thank you for your attention. Thank you for the invitation to the organizers. I'm very excited to see the rest of the day what's going on. And if you are interested to learn more, here's my email. If you're interested to study these things or just drop by our laboratory, you're very welcome. And just shoot me a text and we'll arrange that. Thank you very much.
Yeva, yes, one of our mentors. Чапайте.
So, just an interesting question. I don't know that much about superconducting devices myself, but I was at a talk by Andreas Wallraff, who is, who's someone else in academia, as yourself right now, who's working on superconducting devices in general. A comment he made was that it's a big separation between industry and academia in terms of information sharing with regards to these devices. And I was curious from your perspective, how much of the research is done in academia on these types of devices and how much is being shared openly and how much of the innovation is actually kind of behind closed doors because many of the big players at least in quantum computing tend to focus on superconducting.
It's a great question, and I could probably go on and on about this, but so the angle of academia is that eventually everything is public. So our currency is publications, and that's how we build our CVs, and that's how the success is measured, for better or worse. So in the end, so there is still a little bit of healthy competition, I would say, between different academic groups, where this competition also drives the edge of the state of the art, which actually if it's managed carefully, I think it could be a good thing. And now to contrast with industry, there are different approaches that different companies take, especially in the field of superconducting technologies. For instance, maybe Google doesn't necessarily reveal all their secrets and how they do every single thing, but they do a lot of publications and show the progress that they are achieving, not necessarily from the technology point of view, but from what they can achieve with the technology that they develop. But okay, coming back a little bit more to your question, they do not, for their own interest, for the company's interest, they do not share too much of the technology that they're developing. But as both previous speakers said, there's a lot of unknowns still left that require the flexibility of and customability of the academia to contribute to those developments. And I learned myself, and I joined Microsoft for a couple of years, that it gets very rigid and fixed with when you enter the industry, and so I think combination of both is necessary.
We're in the middle. Any more questions? Okay, so in principle, your team results could lead to new quantum technologies like protected qubits, superconducting diodes, quantum simulators, exotic quantum states as Majoranas, and so on. Which of these applications do you think is most realistic in the nearest future?
So full fleshed out quantum computers, I think, are an interesting destination to have, but I think that's a far destination still today. And so I think that along the way, we'll see a lot of quantum simulators, similar to what D-Wave in Canada is doing, which is applied quantum technologies for very specific problems where you, from the get-go, already know what you want to solve, and you build a device to give you an answer to that specific question, rather than the universal quantum computer where you can think of a new problem today and then use yesterday's quantum computer to solve it. But even before that, you mentioned, and I also mentioned, superconducting diodes, which could be integrated in quantum computer technology, but in principle, it could also be integrated in less energy demanding, so more energy efficient superconducting electronics that is also very, very, very relevant today, especially with the growing usability of AI, which also is a big portion of the energy that you're using today. Just AI is one of the cases, but et cetera. So just, yeah, enabling more energy efficient and more sustainable technologies through superconducting applications is one of the things I think that we're also going to pick up along the way.
I see, it's an interesting path. How scalable is your four-junction architecture? Could be it integrated into larger quantum circuits or multi-qubit platforms? It's like one of your newest papers.
Right. So some of the things, I didn't talk that much about it here, but my angle, it's a little bit, not exactly valley of death, but what my group is doing is sitting somewhere between the material science and then the quantum computing science, and we are building prototypes of potential new types of qubits which could accelerate the progress. So we conceive ideas that then someone else can pick up and use it in quantum science, quantum information science technologies. So I think that's very realistic, but I'm quite biased because I did it. And then the quantum simulators, it's more related to the Josephson junction arrays that I discussed in just studying new types of quantum phases of matter. It's very much related, but a slightly different path.
I see so many interesting paths. Okay, the last question for this session, Šarūnas Miškinis.
I would like to ask you a question somewhere between history and future perspectives. High temperature superconductivity once was ultra-hot topic. What do you think now about the perspective to achieve superconductivity at temperatures close to the room temperature?
It's a great question, and I think there's a lot of challenges. Even though I'm not an expert, let me speculate a little bit. So even the high temperature superconductors, there is a bunch of more conventional superconductors that operate, let's say, at 4 Kelvin, which is a couple of orders of magnitude of than what I'm working at. And the reason why no one has demonstrated superconducting, and it would, if you could get 4 Kelvin or even 1 Kelvin superconducting processors, that would already be a huge, huge achievement. So it's not quite high temperature, for sure not room temperature superconductivity, but there's many, many challenges to be addressed there because one of the reasons why people use superconducting materials is the first slide, or one of the first slides that I showed, the pairing up of electrons. And so you really want all of the electrons to be paired up such that you can describe everything on the microscopic scale. What happens at higher temperatures is that some of the pairs break up, and that results in something that is called quasi-particle poisoning. So that basically effectively destroys the microscopic wave function of just because of additional single particles zooming around. And so already going from millikelvin temperature to Kelvin temperatures is a big challenge. And then afterwards, I think we can start thinking about high TC superconductors, and liquid nitrogen would be already pretty cool. Yeah.
Okay, so let's thank Professor Saulius Vaitiekienės once again. Thank you. Sauliau, to the left, Mantas is going to give the prize. Before we start the panel, we welcome you to join Coffee Networking Break join in the lobby for coffee, informal discussions, and the chance to connect with colleagues from quantum community. The coffee break will last about 15 minutes, so we start at 1 and 10 minutes, yeah? Okay, so we will give you a sign.
I can probably leave.
Okay, I think we are ready to start. So, welcome back. I hope you enjoyed your coffee break. So many of us are still asking, not during our opening session, but still, how close quantum opportunities truly are to real-world applications. And that is exactly why we initiated this entire panel. We will try to answer this question. So we begin our discussion from theory to application, bridging quantum research and real-world impact. We have 5 distinguished panelists. So I will start from the right and go once again. Saulius Vaitekėnas, Associate Professor at the Niels Bohr Institute, leader of the Quantum Matter Lab, known for pioneering work in hybrid superconducting systems and emergent quantum materials. Hi. Yes. We have Evaldas Pabrėža, CEO of Integrated Optics, leader in translating technology into business, heading a company that develops some of the world's most compact laser sources for applications ranging from Raman spectroscopy to semiconductor inspection and even quantum computing in space. Hello. Dr. Ieva Čepaitė, quantum algorithms scientist at Phasecraft with expertise spanning quantum machine learning, continuous variable computing, condensed matter theory, fault tolerance. And as I read, you have a paper authored with Wolfgang Ketterle, Nobel Prize laureate. Wow, impressive. Hi, nice to have you here. We have Jenny Hasu, manager for digital technologies at VTT, actively shaping Finland's quantum and digital technology strategy, contributing to national and European innovation policy. And we have also Dr. Amara Grabs, senior researcher for community engagement and partnerships at First QFM, a former astrophysicist and winner of Europlanet Public Engagement Prize. She now works at the intersection of quantum communication, education, and industry engagement. So thank you for coming. Let's applause for all the panelists. Yeah, perhaps the best question to start is starting from the mismatch. So let's try to ask, would you agree that academia optimizes elegance and theory, as Philip said during his work, but industry wants reliability and integration? What are the biggest mismatches between quantum research focus and industry needs? How can we close them? Yes? So perhaps industry will answer. Let's start.
Yeah, I'll try. I think, well, I think on opposite, but I think that you need some, serial manufacturing robustness to improve quantum systems. That's my claim. So, because especially if we talk about photonics and lasers, I think there's a huge variety of quality parameters and stability that one can make out of a laser. And my true belief is that in the field of photonics and quantum, more stable lasers will lead to more or less errors or more stable calculations in the quantum. So I would say that the industry should focus on repeatability and reliability, leaving the flexibility for the scientists. On the other hand, talking with Philip this morning, he says that the traditions built inside the scientific labs, how to make entangled photon generation more effective and more precise and reach to high fidelities, is giving from older professors to newer scientists, and that's how they nail it, right? So I think there are two ways of perfection. So one perfection is in the quantum process itself, and the other perfection is in the hardware. So maybe let's split it that way, that the hardware perfection comes from industry, and the scientific perfection or the process perfection comes from the labs.
Okay, so Solo, do you agree? Scientific perfection, huh?
I do agree, but before the perfection, there has to be some development in addition before you root into some processes, I think there has to be some development that leads before you can make a decision, and now you can root into those and start building rigid processes. And as was highlighted a couple of times in the morning session, no one really knows for sure which of the technologies are going to emerge as the winners. There are some front leaders at the moment, but other technologies are not far away. And so I think there has to be quite a bit of collaborations between industry and academia. And it's not that they're absent. There is a lot of programs. European Innovation Council is one of the example instruments that enables stuff like that. And so fostering these collaborations is a good twist to the whole.
Talking about science transformation into business and real cases, quantum algorithms are pushing it forwards. So maybe Yeva can comment on this question. Yes.
Yes, I think a slightly different perspective from the software side, which is that I think quantum computing in particular is a field where I don't think it makes too much of a difference if you're in industry or academia with regards to the research. I think the motivations might be ultimately slightly different in the sense that, you know, in a company or an industry, you're beholden to investors and you need to find a way to commercialize what you're working on. But I feel like to some degree, a lot of academia has now moved in a similar direction, which is that a lot of grants focus on applications of the technologies that people are working on. So in my experience, I think maybe with regards to hardware, it's a slightly different path, and I can't speak on that. But as a researcher in industry in this field, I find that I end up doing just as much blue sky research as I did when I was in academia. So I feel like in such a fast-growing field, and especially with a lot of startup power, which tends to have a lot less, you know, large-scale administrative infrastructure, kind of holding it back or directing the workflow, you end up not seeing too much of a difference between industry and academia.
Nice to hear. And what is the biggest mismatch between quantum research focus and industry in Finland? Jenny?
Well, without infrastructures in academia and RTOs like VTT, most likely our industry sector in quantum would look very differently than it looks at the moment. So I feel that there are different paths of growing, and we can either take the old paths or just say that no, we are going by ourselves, and usually we know how it ends up when you go by yourself. So it's quite clear that there need to be infra if you are building a new industry. And someone, usually in this case, when it comes to quantum, and it's quite costly to build new infra. It is quite nice that the governments, states, EU are doing it, because then they are helping the growing of the industry. And we need all of them. Yes. So I wouldn't put them in different boxes. So I'm very keen to know all the quantum software that's coming into market, because in the end of the game, most likely the big money and the money is always something that we need to follow. Where the money is going is coming from a software in the end.
It dictates the rules. Yeah. What is the situation in Latvia? Yes, Samara.
Okay, I'm not as deep in the Latvian, like University of Latvia about this. What I want to comment is some of the mismatch and where it appears. So, for example, there's a timeline where research is longer timelines because of the funding. Usually your grant proposals are like 3 years, 4 years, you know, and so 2035 or 2030, well, 2030, you know, grant proposals, whereas startups are 6-month, 12-month, 18-month runways where you need to get something in return really fast. You don't have such luxury of time in that. And then there's a metric where the researchers are talking about those details like qubit fidelities, and founders need revenue streams, KPIs, partners, customers, like really fast, and TRLs also. And then the problems, so in the research lab, it's very messy. and you figure things out. Whereas in for companies, it is right now simulations and toy problems because you have limitations on the hardware. So that's the mismatch that I see. And how to close the gap would be mixed teams. Researchers, startup builders, mentors, they can co-design roadmaps. Have you thought about that? It's kind of mixing the different parts of the quantum ecosystem where you have the startup companies talking to the research labs, talking to the policymakers, talking to the industry, and this mixing is glorious. And when you can get that reality into your roadmap, then that's one way you can close the gap.
Yeah, I agree on that. I agree on that mixing would answer several questions. We talked now about lab, about tech. Let's talk about people. So are we producing the right kind of talent? People who bridge physics, software, and business are still training too narrowly. How do you think? Yes, who wants to start? Saulius.
I have a very specific perspective from the academic point of view, especially being an experimentalist. And my view is that with the growing interest in quantum computers and other quantum applications, the traditional Blackboard lectures are a little bit growing out of date. Not completely, I mean, we still need a bunch of those, but I think we should strive for more hands-on training, which, for instance, in Copenhagen, we are developing a lot at the moment and investing heavily. So it's not that we are going the wrong direction, but a small correction towards more application and experiment-oriented training and not replacing all the curricula, but expanding or adjusting a little bit is needed at the moment.
Yeah, so quantum mechanics on the Blackboard, it's not enough. Yes, we need more. Jenny wants to comment on that.
I totally agree with you. And do you know what is the hidden secret in Finland when it's come to quantum? We have a quite working clocksmith school, kelloseppäkoulu. And many people that works in IQM and in Plufor, for example, have went to that school. It's more school about applied science than a school of higher education. So we have seen that we need to have all kind of educated people from quantum. And the Clocksmith School is always in the present when we are speaking about the workforce of quantum needed in Finland. And then we come to the questions of appliance science, higher appliance science schools and universities, and even at BTTO, even though we don't have the premises of giving lectures, but we have PhD students in VTT that we pay salaries. But yet again, at this moment, it's not enough when you saw our vision and where we want to target ourselves, not only in Finland, but in EU in general as well. We need to have more joint understanding what we want to achieve in this agenda when it comes to education.
See, so how Phasecraft or Integrated Optics finds people to work for them? Okay.
I think we're in a bit different world. So as a component producer for the quantum, we source talent and just people for production in the old-fashioned ways. So I think in total for the quantum to thrive, I think it's not about the quantity of people, it's about the quality, or about those who can think out of the box. Because the phenomena and the key principles, key effects are already discovered and clear. It's just how to apply those effects and principles in a non-standard way, not following the heritage of classical computers and not following the heritage of mechanics or any other fields, just creating on its own, like a new concept, a new jazz improvisation, that that would lead to employing these effects for a completely new result. So I'm talking for the company, so we'll stand by and wait patiently until these breakthroughs appear somewhere in the scientific field. And we will, meanwhile, we'll be doing a lot of other applications like life sciences or even defense, whatever. But with the idea that the base that we build will be useful for the quantum manufacturing or manufacturing of quantum devices once these breakthroughs are available.
Okay. Yeva.
Yeah,
Yes.
I completely agree on the quality of talent that is required. Actually, one problem that we have at Facecraft in particular with regards to hiring is that there's a ton of grads coming into the field right now. It's booming, it's very popular. We have no one senior. It is really, really hard to find people in the field that can actually lead a team or lead research, because obviously in order to do that, you need more experience, you need to have been in the field for longer, and that's just not the kind of people that are around right now. So actually what we're hoping for is obviously all these grads that are coming out now in a couple of years will be a very, very fantastic workforce, because in such a technical field, you need people with a lot of technical experience. And unfortunately, even if you're really bright, usually for the type of research we're interested in doing, theoretically, a master's tends to not be enough, just because you don't have enough experience in a particular subject area to actually end up doing the kind of work that we need to do. So it's great that we have more people coming in. I think it's relatively easy to do sort of parts of research in quantum theory if it's not direct research. So if you want to do software development adjacent, you can do that, very easily now, regardless if you're just a bright student. But if you want to lead research and really move the field forward, we need folks with a lot of experience and have a high quality candidates. Yeah.
I have one more additional question for you. So in classical programming, you have junior, senior, mid and seniors, and they have a span of, I would say, 5 years, maybe between one and the other. What's in quantum?
Oh God, it's hard to say. I think it's more specializations that are the issue, right? So yeah, if maybe even a few years, a PhD tends to be enough to build up quite a lot of experience already, right, for most things. But if you just didn't happen to work on the kind of topics that are important to whatever the company's doing or whatever the group is interested in, then it doesn't matter how much experience you've got, right? That's the other thing. So I don't know about how much time, but it is true that you need to build up a lot of expertise in particular topics.
I think it was similar in artificial intelligence field. Also, we should grow from the beginning. Amara, would you like to add something?
So there's two kinds of people that I think will help the field. One is what I call triple helix people. These are those who can move fluidly between business and research and education, and maybe a little bit of policy. And then there are systems thinkers who see quantum as part of a larger system. So they can see all the moving parts, like the modalities, algorithms, error correction, network. And so they see the interconnections, a big picture. This is, so in quantum, they see the whole system and they can imagine the outcome of all of those moving parts. And this is an experienced person, whole brain thinker, maybe those dyslexic whole brain thinkers that companies love to hire in the visionary parts of the company, So, and then the triple helix people are those who move the communication between the different subdomains and to make sure that the businesses are abreast of the latest education, and the education is keeping in touch with, let's say, what the latest funding round, or it's the triple helix people are not necessarily trained in quantum, but they have a deep tech background, and so these are the two kinds of people that I think are missing, and you can build that into the education system. Like, for example, you can make sure that your student projects, you have them thinking like a product developer, like how do you want to deploy this once you have this implemented? Or, I had a really interesting comment from one of the IQM founders. He says, I want to have people who think like they're product designers, you know, not just researchers, but they can visualize the product at the end.
I see. Okay, so if we talk about quantum, we see the tendencies that it's getting more and more popular, even at the conferences. It's so difficult to get a time slot to give a public speech. It's such a contest. And each year we see new, fresh discoveries, ideas, like Saulius presented, so on. But from commercialization perspective, what slows down translation of quantum research into products the most? Is it funding? Is it lack of real use cases? Or something else is missing here? Yeah. Okay, yeah, about the most brave one.
I mean, for a quantum software company, we don't build our own hardware. We rely on hardware providers. And obviously what we need is just better quantum hardware most of the time. We have some ideas for what to run on it. We just haven't been able to run it half the time. But obviously the other side is, you know, part of what I do, my job, and part of what a company does is we need more work on the software side. So I don't know if this will translate to one of your, you know, whether it's funding or IP. I suppose it's just a concerted effort of closing the gap between what the hardware can do and what, you know, the software side can do to reduce the time, you know, reduce the resources needed on the hardware to implement something, basically. And this is from a quantum computing perspective. I actually know that in many other sides, like quantum sensing and stuff, I'm less familiar with actually what's required there. So I think just getting more people thinking about both of those sides, basically, yeah. That probably makes the most sense. I know it's a very basic cop-out answer, but it's the obvious one, which is that we need better hardware and we need better algorithms that require less hardware to run to get a nice use case out. So.
Okay, so basically Jeva needs hardware. Who else would answer? Jenny, yeah, what do you need?
Yeah, it's really nice to be in the conversation because usually it's either it's only the hardware discussing about hardware or software discussing about software. It's really nice to speak about the both at the same time. While we were doing our national quantum strategy, we invited to open discussion companies that are either Finnish that are located in Finland about what they're expecting from quantum. And because it was a public hearing, I can speak about it. There was 50 companies in presence. And what we learned from that the expectations were still rather moderate. So they didn't know much about it. They didn't know what they would gain out of quantum. Like what is it for me? Why should I invest to quantum? It doesn't matter in this point if it's software or hardware because we started from the very low key about we started what is quantum and how this might change for your perspective. So I say one of the key questions, well, we have seen that there is money is moving, yes, at least somehow. We all know the lack of talent, that's a problem. And the one problem is the courage. That is a word that is missing in many cases at the days of that we are living now. But we are hoping to see someone to take the lead. Okay, we will invest heavily on quantum software. We have seen invest heavily on quantum hardware, but we have not seen this maybe yet.
So it's like a risk-taking path. Amara, yes?
Yeah, so funding across the Valley of Death, we all know this. Okay, and so there's something else I want to say, which is about timing and communication with the user community. So anytime there is a press release, there's 3 groups of people that are engaged. One is the STEM literate public. They go to Wikipedia and they look up something. The other is the deep tech community who are skilled in technical areas, but not necessarily in quantum. And then the third is the expert quantum people. And anytime there's a press, there's different ways of engaging them where you need to have a credible message and engaging them. And the timing has to be such that you don't lose your credibility. So there's been big company press announcements where they didn't address carefully the past years, maybe 3-4 years of results that were not good for the company. And so they made a number of press and then went to APS and filled an auditorium with this particular quantum technology, and they talked at the audience instead of with the audience. They didn't give time to have those expert people give questions so they could answer the questions. And so then Nature came up with what followed that APS conference, and it didn't relieve the anxiety, of the the expert community who really wanted a credible answer. So I think, if you're in a company, you have to educate your community as you're able to. You don't want to release IP before it's ready, but you have to bring your community along with you and be aware about these 3 different communities.
Okay. How about integrated optics from commercialization perspective? What slows down you? Is there nothing?
Yeah, I keep being surprised about how risk tolerant are some of the investors in the field, especially in the US. I think you would not imagine such risk tolerance and such early stage investments a decade ago. So I think this is already exciting. Of course, it could lead to some bad experiences if we are too brave and too early. Remembering the dot-com bubble or something like that. So
Overconfidence.
that could also happen. It's not something that we should totally eliminate from the discussion, but it doesn't change the fact that we still need to make a good strategy to move forward and really address the questions that are not addressed and answer clearly. And also, hopefully, the investors, they will not, they will keep being interested in the field. They will still feel that this is a revolutionary field, and that finally we will have a good match between public and venture capital funding, which is essential. I mean, you hear about the amounts invested in the companies, and it's huge actually compared to the either financial results of the companies or whatever. But so just let's hope that it keeps this way, and we have enough patience to await for the result.
Okay, so patience is the answer. Solo, are professor interested in commercialization of their research? You're a nice example, working with Microsoft and so on.
I think they are, and that's actually also the angle that I wanted to take on this question, that we are talking about very advanced topics that one cannot just read up quickly and start a company. One studies it deeply, and in order to be able to lead a group, one needs a lot of experience, and so a lot of the quantum technology companies are emerging from people who are trained in academia. And there are many good examples, but academics are a specific breed that once you get to the point where you are mature enough, where your thoughts are mature enough to lead a company, you're also trained in this academic way of thinking, which has a lot of freedom. And so people are often reluctant to give that up. That's one of the reasons why I also came back to academia from industry. But there are still good examples, and honestly, I think that there are some gaps to be closed, but they are being closed, and at an okay rate. There is a lot of quantum hype, so I think that needs to be slowed down a little bit, which maybe will leave a little bit of room to closing in all these gaps. And Philip was talking about his satellite products, etc. And then there's all other sorts of applications, both superconducting, photonic, and whatnot, and they are emerging and they are being developed, and focusing on that. And I'm pretty confident that most of the gaps are going to be filled in.
I think in your answer you mentioned a really important thing as a hype. So because a lot is happening, but still quantum mechanics sounds from mystery. How do we make quantum research visible and relatable for society, for investors, policymakers, without overselling it, without this hype? Could you help? Yeah.
Maybe, yeah. I try to step up into the shoes of investors and try to understand how they think. So I think they try to estimate the total time span until the technology will be useful. I mean, there are quantum technologies which are implemented, like quantum clocks and everything. So that's a good kind of background or
Foundation, yeah.
status quo foundation for this. And then they estimate, okay, maybe it's 10 or maybe less years until computing will give some benefit. And I think the typical terms of the venture capital is 5 years. Maybe some patient capital is 10 years oriented. So I think most of those who invest at the moment, I think they still think that, okay, in the next 10 years we'll manage to change hands to other funds or to make the company public and then exit that way. So I think I might be wrong, but I think it's still the situation that the investors are thinking about near-term exit or change hands of those companies before it will become a kind of commodity. So, but we'll see how that goes. Some companies who went public are quite successful. They have lots of money. They can do a lot of acquisitions. Even I think if one of the companies would come and say, we want to acquire your company, which makes lasers, which is essential for some of the quantum applications, I think I would join the ride, like to agree to join a bigger quantum company, but that doesn't eliminate all the questions.
Okay, so now we heard insights from investors' part. Let's say, if you talk about society, Ieva, you were popularizing a lot quantum research and in physics today, and you were talking. Yeah? So from your perspective.
I think it's hard not to be excited about quantum technologies because it is the frontier of what we understand as humanity on that side. And I think, anyone can get excited about this. With regards to hype, I think it's impossible to overhype the science. I think it's possible to overhype the commercialization. That is definitely true, right? Because you need to make actual concrete promises to people about what you can and can't do with the technologies and what, how their lives will be impacted by it. And I think the way to straddle this is as we've straddled every other big technological breakthrough in the past, which is, you gotta try. You gotta put everything you can into it and see whether or not it leads to any breakthroughs. I mean, there's a lot of nice theory and the technology, like the actual tech side, the building of these devices and all the components to do with them is really, really hard. Doesn't mean it's impossible, but it is really, really hard. And I think a really good way of balancing out the excitement and this caution is to be extremely open about it and to have very good narratives for people about what it means to build this, to sort of temper any over expectation, because I think as a researcher, despite being in a company, I think my work gets harmed a lot by hype. It gets harmed because I don't get to work on stuff that actually could work or would work because someone is expecting me to do something that I find, if not impossible, then at least improbable for a very long time to happen, right? And if they have these expectations and we don't deliver, then the plug gets pulled early. So it's important. I don't know if I've given a good answer for how to address this, but I do think being extremely honest with both why I'm excited about it, because I'm working in this field. There's a reason I'm here and there's a reason I want to keep working on it, but also to sort of be extremely honest with what the difficulties are and kind of actually talk about them instead of just keeping them under the table most of the time.
So we heard about the consequences of hype
exactly
on your spacecraft. So we have here expert on quantum communication intersection, Amara.
Yeah, so actually this is my largest answer section, but I condensed it successfully. So use the narratives, be realistic, connect the dots. That manages to keep the excitement, but you can build guardrails against the hype, make sure that you show the evidence, what are the tests, explain what we don't know yet. You don't want to say that we'll solve climate change tomorrow. Really, please don't. You have to have a timeline about what sort of conditions you need for your hardware and software to solve those kinds of problems. And so that's the being open and being realistic. Now, if you talk to policymakers, that's a little bit different of a category of communication because they don't want to know about fidelities. They don't understand what that means exactly unless they're tracking very carefully the fidelities of the qubits. What they want to know is what impact that will make on industry and your workforce and security, of your country. What dependencies does that research have? Where in the research system does your discovery lie? They need to see the big picture. So that's a different kind of communication. And then for press releases, my gold standard of press releases is to show your paper, your research paper, and then a condensed version for the less technical readers. Then maybe a video. You want to compare what the previous research result had and how your result compares with that. And I guess those are the main points. So just data evidence, that's a way to remove the hype.
Jenny, is the hype high in Finland?
Well, yeah, it is. And it is hype, and I think hearing all of you is quite understandable why it is hype. I think it's quite understandable why it's hype all over the world at the moment, because everyone is seeking a solution for the problems that are very difficult, multi-problems that nobody has the answers. And any nation states would love to be the one who says, yes, we have the answer for climate change or hunger questions or whatever, and they don't have it. So expectation management, it's very difficult, and I think it's going to be even more difficult when new outcomes come. They do all the time. Researchers make great works, and still people are, but about the climate change was not there yet. Why? So we need to make more work together as well as explain quantum. That's why I say, and I hope that nobody understands it wrongly, that quantum computer itself is not revolution. Because many times when Finland, we have a press release that, yes, we have a new quantum computer, people are like, yeah, finally. We are there. And no, it's just for the beginning. So I think we need lots of cooperation with different actors, and still it's going to be rather difficult to manage the expectations.
Yeah, small steps.
I want to add one quick thing before I pass to Solus. I just recall that one of the co-founders of my company, I think he said a really, really nice sort of thing in a presentation that I watched a while ago, and he was like, Facecraft, our company has been around for about 6+ years now, and basically since then, even in these last 6 years, there's been some peaks and troughs basically in terms of hype with regards to quantum computing for various reasons. And I think the way he described it is, we started out kind of being pessimists because everyone around us was super hyped about the tech. And then after a few years, everyone else kind of got really, really down on it. And then we look like optimists. And a couple of years later, once again, we look like pessimists because everyone's being hyped. So the whole point is to kind of keep it steady, keep your expectations, about as level as you can with regards to what you know. So sorry, I just wanted to say that because I think that's how it feels half the time in this field. But yeah, I'm sorry.
I don't have much to add, just maybe very briefly, is that events like this and then keeping our opinions grounded and then communicating between the industry and an academic who has a little bit more sober take on the whole matter are very useful. And based on history, things are self-correcting. If there is a company that makes a big claim and an announcement, and then there is a backlash from the community, media also picks that up and corrects it. And maybe doesn't reach the same audience as the press release does, but there is still self-correction in the whole process itself. So I'm optimistic and I want to trust that process.
I see. Okay, we are approaching 2 o'clock. Finally, it's going to start. But to end our discussion, like a question, and I need from you 1, 2 sentences, like short answer and inspirational, motivational note, just to end this panel discussion. So, in your opinion, will we see quantum winter or quantum spring? And what's your dream first commercial quantum success story? Who wants to start, or we go one by one from Solus?
If I weren't optimistic about any of this, then I wouldn't be working on this. So I'm more leaning towards a quantum spring, and the thing that I'm looking forward to is the serendipitous discoveries of things that we haven't thought of yet. In some sense, repeating the story of the regular transistors that enabled the technologies that we have achieved so far, but then enabled through quantum mechanics.
Evaldi?
If you cannot trust human, then you can maybe trust photons. So that's my takeaway.
Captivating. Yeva?
Trying to be optimistic. I think quantum spring, and in part because just in the last year we've had an awful number of so-called quantum advantage papers.
Yes.
And a part, in my belief for this, and why I say quantum spring, the reason I believe that there's been so many is not because companies suddenly need more PR or something, or these researchers need more PR, and so they're going, look at us, it's advantage. It's actually because the hardware finally got to a stage where you're probing the edges of what's possible classically, and you're starting to see something that you couldn't do otherwise quantumly. So we're actually now at the cusp of things that are becoming interesting. So I'm quite excited. Yeah.
Nice. Excitation, photons. Okay, Jenny?
I'm excited as well. I believe in spring in many ways when you look outside this point of the year. Quantum materials is something that we have been following quite closely. So I'm very hopeful that something come out of it.
Okay, nice. Amara, the final.
Quantum spring also, for all of these same reasons. And then my dream project is quantum drones, especially in this region where we live, because the
Baltic is
drones exist, and why not augment that with some fantastic quantum technology?
Yes, nice, nice. Thank you for excellent discussion. Let's give a big round of applause for our panelists. Thank you. Thank you so much. You can take your seats. Now we are moving into our final part of the event, grand finals, top 6 teams, presentations, and jury evaluation. So I will now kindly invite the jury members to take seats here in the front row. So we will start. Professor Mantas Šimenis, professor at Vilnius University Faculty of Physics, head of the Electron Spin Resonance Laboratory. Hi. Dr. Tadas Paulauskas, senior researcher at the Department of Optoelectronics, Center for Physical Sciences and Technology, FTMC. Hi. Professor Remigius Paulavičius at Vilnius University Faculty of Mathematics and Informatics, head of the Blockchain and Quantum Technologies Group, vice president of Quantum Lithuania. Hi. Dr. Karolis Stašys, head of Innovation and Technology Department, Center for Physical Sciences and Technology. Andrius Milinavičius, general partner at BSV Ventures. Hi. Here. Yes, evaluation tables. And Victoria Trimble, managing director at Coinvest Capital. Hi. Okay, so jury is here already taking their notes. So after each team presentation, we will kindly ask jury members to provide a brief comment or a question for the team. It will be like a talent show, so prepare. Uh, now the most important part, pitches from the teams that have reached the grand finally. To open this segment, yes, and talk what they tackled. They tackled a lot, wide spectrum of problems from GPS independent navigation, quantum secure communications, etc., etc., etc. And their work has been guided by outstanding mentors from Spacecraft, from Qnesis, BSV Ventures, Coinvest Capital, Vilnius University, and Kaunas University of Technology. So 3 teams will join us virtually, and 3 are here on site. So we will start from the virtual ones. The first team, HJKR Superposition, joining virtually from Riga Technical University from Latvia, presenting their solution to the Quantum Secure Navigation Challenge. Do you hear me? Yeah?
Let me share this presentation.
Okay.
So, yes, greetings everyone. Today, GPS underpins every critical infrastructure, from aircraft routes to shipping lines to mobile networks. But GPS is vulnerable. Jamming and spoofing is a daily reality for us, and also a looming quantum computer threat will make our current encryption measures obsolete. That's why our team, HJKR Superposition, has provided a solution for securing navigation for the quantum world. My name is Richard Smurnieks, and I'm excited to present you our solution. So what is the actual problem that we're trying to solve? So GPS is a single point of failure. Jamming and spoofing are easy targets, and our transport infrastructure gets vulnerable. Also, synchronization networks are assisted by GPS, so they run these 4G and 5G networks. That's why when GPS fails, communication fails. And it's a dual threat to navigation and to synchronization. Our solution, proposed solution, is a ground-based navigation system enhanced by atomic clocks and quantum encryption. First, atomic clocks, it's basically a high-precision clock that provides a time information to the navigation and synchronization needs. We also suggest encrypting optical network segment with the quantum encryption, and also encrypting wireless network segment with quantum encryption from antennas to, for example, aircrafts. And we have also validated our solution. Here you can see this scenario. The red box is the air corridor where the airplanes approach our capital Riga airport. And the blue triangle shows the possible antenna placements for this scenario. So somewhere in the middle of the triangle is an airport. And we have shown through the simulations that the optimal spacing between these antennas are 100 kilometers, and the precision that we can achieve is 1 to 2 meters in the middle of this air corridor near the airport, where the most important thing, landing of the aircraft, happens. And the solution cannot work just by installing the hardware. So what we propose as a part of here is a software platform that would orchestrate everything, every hardware piece, to work in a coherent system. So we will provide a platform. There are 2 product options: hardware plus software, where hardware is provided from the hardware providers. It's market-ready, off-the-shelf product for ready to be implemented tomorrow, deployed tomorrow, and and the software. And here it's important that software allows a defensible IP. We can also build the software in a modular approach. So the idea here is that we can provide hardware from hardware providers that we have, or the clients can use their own hardware for these software modules. So it basically allows solving the certification issues which happen in between different regions, for example, EU, America, Asia, and so on. Yeah, so that's why we provide alternative to GPS solution, full stack navigation and timing platform, which sits, our segment sits within the 3 to 6 billions of TAM, and it's around 5+ billion serviceable market, which includes transport, telecom, energy, and finance. And by 2030, with our hardware plus software solution, we aim to penetrate 5% of the market, which amounts to around 250 to 350 million in potential sales. And to use this opportunity to bring revenue, we propose a B2B and B2G business model. Our customers would be airports, airfield operators, telecom network operators, and governments. For example, recently, UK, US, and South Korea have been investing into similar ground-based navigation systems. And potentially, we can also cover other critical infrastructure operators where synchronization is important. It's energy, finance, and data centers. We would offer, as I already said, two possibilities: hardware plus software, where the scalability for our solution would most probably be EU plus some partner countries, and software, which would allow instantaneous global scalability. The remaining revenue streams would be multi-year contracts, recurring software revenue. We can also host our software in the cloud, so it would be cloud subscription revenue. And we can also give licensing to integrators. Yeah, but the question here is, why would customers adopt our solution? And there are multiple reasons. First is that it's a full stack approach. We leverage multiple market-ready, off-the-shelf, well-known and novel technologies into this full stack solution. Second, we reuse already existing infrastructure for fiber and mobile networks, so it will reduce the investments necessary into the infrastructure deployment. And yeah, so the key point here would be that our system could provide both the synchronization and navigation. Third, we would reduce risks. Jamming would be overcome by using strong signals. For example, because aircrafts, they are closer to antennas than to GPS satellites, and spoofing would be solved by encrypting this with quantum resilient encryption. Actually, current commercial GPS signals are not even encrypted with classical encryption. And finally, the fourth, maybe one of the most important, is obtainable precision. We offer navigation precision of 1 to 2 meters. GPS navigation currently is 1 to 3 meters. And in addition to similar current ground-based systems, like in comparison to them, we provide tenfold precision improvement. Our team is perfectly positioned to bring this this solution to reality. We have 3 PhDs, where 2 of them are assistant professors, 1 is associate professors, where each of us have at least 10 years experience in the telecommunications systems, networks. And we also have a master's, a talented addition to the team, having 4 to 5 years experience in the telecommunications field. So we actually know how these communication systems work. And this experience, this core team experience, speaks for itself. And combining everything mentioned, we come to the result: a full stack defense in-depth GPS system alternative or fallback option, resistant to jamming, spoofing, quantum era cyber attacks, and provides secure navigation and synchronization. It can also be offered as a synchronization-only service. So the main 3 steps now would be, first, validating the solution with live weather data, and for example, in combination working with aircraft inertial navigation systems, for example, under sophisticated jamming and spoofing attacks. Second would be building hardware agnostic software with modular approach, allowing to different hardware for each module, and then also testing the build software. Of course, all of these 3 steps would also include a lot of subtasks. So here we are. We are ready to build. Let's make quantum resilient navigation and synchronization together. Thank you.
Thank you, AJKR Superposition. Nice presentation. And now we start from discussion with our jury members. Andrius wants to ask a question, yeah?
Yes, Richard, thank you so much for a very clear and concise presentation. I have a lot of questions, but I will try to narrow down to one from my side. Can you walk us through towards the competitive landscape? Obviously, you had a discussion here. So if the problem exists, what are the solutions that are being used today, and how are you better, just in a simple words?
So today, there are already existing competition in the field, but most of the competition focuses on a small part of the system. For example, using quantum sensors for navigation, really simple. But how we are different, we are proposing this platform, the full platform that could actually incorporate those small offers for quantum sensors also. These offers into the ecosystem. So basically, it's not just some kind of small platform specific for quantum sensors, but it's full stack platform, this system. That's how we are mainly different here.
Okay, Victoria Trimble wants to ask.
Hello, everyone. Thanks for presentation. But first, I have a question to organizers, just to make sure we interpret in the same way. So, in the valuation range, what is the best, number 1 or number 10?
Number 10.
Okay, good. And the question to the team would be about your business model. If you could reiterate a little bit more. This hardware aspect, do I understand correctly that you are going to be like a reseller of hardware, but your main product is software product?
Yes, so if I heard the question correctly, maybe, then the hardware that we are actually is already existent, it's market ready, off-the-shelf products for quantum encryption, for QKD, for PQC, and it's also, but the software is actually the thing that makes this all enabling technology. And the software is hardware. We cannot have an IP with that because that's provided from the hardware providers. But we have software which is main defensible IP, and it's actually also more easier to scale. So yeah, I know if I answered the question correctly. There was some kind of noise in between the question.
Karolis Stashys.
Okay, I have a question. Let's take, for example, an airplane, which is using your system to navigate in a dangerous environment. Does that airplane can use its own embedded GNSS system, or it needs to add additional system? Can it use the one made in the factory?
Yes, in this case, if the aircraft has its built-in GNSS system, for example, inertial navigation system, but it still needs some precision signals to adjust it because there are drifts in the precision where they can navigate. So having the signals from the ground, from the mobile network antennas, where the navigation antenna is positioned, you can just send signal to the airplane, and the airplane can use it to recalculate its position and then continue with its way.
So if I understand correctly, you need to install additional hardware to the plane to use your system?
No, actually, the plane can use the system itself that it has already. It's the same principle as GPS works, but only from the ground. So we provide the same services, like similar services, but from the ground. So basically, it won't need any new systems installed. There is my team member on this. Maybe he can say something more.
Yeah, to complement Richard's answer, technically, yes, the different receiver is needed because we rely on eLORAN system from ground part, but the rest of the calculations, the triangulation calculation is pretty much the same as in GPS case. Yeah, but the different receiver located on airplane's belly, not on its top part, would be required in this case. Yeah, that would be hardware part additional.
Okay, Remigijus Paulavičius.
Hi, thank you for presentation. As we need to evaluate innovation level and scientific level, I have one question from two parts. First, I know that Latvia is already participating in EuroQCI. Recently, Techritory, you sum up what you did in the 3 last years. So my question, is this solution originally proposed for this Quantaton, or it was adapted, let's say, from your previous experience which you gained from EuroQCI? And the second part, is this proposal was already somehow scientifically validated in scientific publication or conference, or it's just really new concept which you're presenting first time here? Thank you.
So this idea is obviously built on the previous experience in this EuroQCI regarding QKD, but in this case we adapted a little bit different approach because current QKD systems, for example, they work on a transmission of this quantum state, but we actually would employ quantum entanglement leverage here. So actually, the key information wouldn't be transferred over the channel at all. Yeah, so that is the first adaptation. And also, an atomic clock, it's a new idea that was just submitted to one of the projects, but it's basically this offer is completely different. Yeah. It just brings some ideas of previous projects together into one coherent system. And no, it hasn't yet been published anywhere yet for validation. Validation was just made for this Quantaton in simulation validation. Yes.
Thank you.
On this, yes, please.
Yeah, in short, it's not been published anywhere by ourselves. We just what we rely on existing things. eLORAN system is known before us, and QKD is known before us. What we bring together is eLORAN and quantum clocks plus the software part which overlays the whole system. Yeah, but yeah, it's never been published everywhere, and neither been a result of any project so far. Yeah, that's in short.
Yes.
Okay, so are jury members satisfied with the answers? Mantas Šimėnas once.
Hi. Thanks a lot for a nice presentation. I have a question regarding jamming of the signals, the communication with the airplane. Is your system immune to that? If yes, how so?
So our system is not completely immune to that, but it actually it provides stronger signals, multiple times stronger than signals coming from antenna. So that's the one thing, because it's so easy to jam the signals at the moment because they are weak, and you don't need a so much strong receiver. And in this case, we would use much more energy, and it's around 100 kilohertz frequency. So it's basically it would require a huge station for anybody to jam this. So a military-grade equipment. That's actually would be a huge challenge. It would require immense energy for anyone to do this, to jam the signal.
Thanks. And another question: do you really need quantum encryption? I mean, to send some information to the plane, which is I assume a passenger plane, for example.
Yes, you need encryption. Why? Because spoofing happens. Spoofing is basically sending the signal, similar signal to GPS signal, to the airplane. But how to solve it? It's using encryption. So airplane actually knows where the signal comes from, and it can trust it. Because otherwise, it can receive a information. For example, airplane suddenly is going into the mountain. Yeah. So that's why the encryption is really important here.
Final question from Tadas Paulauskas.
And last question. First of all, thank you so much for a nice presentation, nice full stack approach. How scalable is this approach? You basically, one of the key ingredients, you'll need to lay down radio tower emitters. Is it a regional solution? And can you use some of the things already that is there, infrastructure, etc.? Thank you.
Yes, so as I mentioned in the presentation, it's first we reuse all the deployed infrastructure. It's fiber infrastructure, it's mobile network base stations. We actually propose to use mobile network antenna sites to host our navigation antenna, and that's the first. And actually the software, this full stack software approach, it allows us to scale it pretty simply. You can basically use as much antennas as you want in your network. You can place atomic clocks like as much as you want them, as many as you want them. For example, you can use the central hub. Actually, it allows to host a lot of antennas, a lot of atomic clock sites. Yeah, so it's easily at scale.
Okay. For example, I was surprised to see that atmospheric effects contribution was really that small. It's interesting to see how would you develop it in the future. So let's thank for AJKR Superposition for their presentation and answers. Thank you. Okay, we are moving on. Second team, Quanture, joining virtually from KTH, Royal Institute of Technology, Sweden, presenting quantum network navigation, the Quantum Hyper-Steiner Optimizer. Yeah.
Can you see my screen?
Not. Yes, now it appeared.
Loaded, right?
Yes.
Perfect. So, hey everyone, we are Quanture. We assist navigation with quantum technologies. And I want to start this presentation with a personal experience that I had. A few months ago, I took a flight from Stockholm to visit Tallinn in Estonia. I was really excited. And before landing, the airplane started to diverge. That's where the pilot made an announcement and said, "We are being jammed." So that was the first time to think that this jamming is real. And the emotional and psychological impact was visible on the passengers. I hope there is the, yes. So this incident is far from being unique or rare. Actually, it is growing very fast. So from 2023 to 24, we have a plus 65% increase of these incidents, 5 times in those last 5 years. So this accountability, safety, and financial stability is really threatened today. And from the official UK government website, actually, you can find they estimate 1.4 billion pounds is the cost of GPS outage during only 1 day in UK alone, which is huge, phenomenal. So what we can do about that? So the jamming issue is inherently systematic to the classical system of using our satellites with radio frequency signals. And to solve it, from being unsolvable in NP-hard, let's say in mathematical language, is to change the system to be fully quantum. And here we leverage the quantum effects and we abandon these jamming issues. Of course, it will not being naive, it will of course open a new quantum hacking, jamming that we don't know yet, for example, but we can close them. But at least those are very far and much harder than jamming itself. But in the same time, why do you want need to this transition today is because those quantum technologies are commercially available. We have quantum sensors. We see a big investments, IBM and Google into quantum computers that are now today available, even though they are faulty. So from this transition, we want to position ourselves in this hybrid classical quantum transition inevitable. So from this ideal, if we can back in this transition, it of course will have some milestones. It will not be continuous. We will add and remove certain things, right? And what we can use today is not remove our satellite. We can keep them, use the AI that is now very nice, and those first order or first version of those quantum resources, especially that those quantum sensors have still drifts. They have a swap constraint, which is like size and weight constraints, and they still need some periodic synchronization, and this synchronization also link, they're not maybe fully quantum and so on. So what we propose here is within Quanture is this CARE, Quantum Assisted Resilient Engine. So this has the ability to combine those classical resources, right, with the quantum resources, right? So those classical resources that we already have, this RF and the computing, but also in the quantum resources that are the sensing, computing, but also networking, right? So this is hardware, this is software to assist the hardware and optimize the best use of those combined hybrid resources. We don't have fully quantum, we have a hybrid one. So we have to optimize, find when and how and what to connect to minimize, let's say, finally, a cost, which is the drift from the due to a jamming, for example, event. And within the CARE, we see it as have an architectural layer. So one of the layers that was actually our hackathon focus. So we focus on a layer, which is like an algorithm that we thought to run it into a quantum computer that is an edge computing, let's say. And it uses a part of quantum, which is the quantum assisted optimization algorithm. So it's also a hybrid classic quantum still. But why we do that? But because that's what we have today. We have faulty quantum computers that are not fully fault-tolerant. So that's what we can do today. So this is a layer. And so we see CARE as also a software that is an adapting dynamic to these milestones during this transition. So it's combining this classical inertial navigation system with the quantum measurement units to optimize and stabilize our quantum navigation. It seems that yes. So for the competitors, there are very few, obviously, and the most prominent one is quantum control, Q-Control. So actually, recently they got a lot of attention, even Times Magazine. It's just because they could optimize or characterize the quantum sensors using machine learning outside, like edge computing, but it was a classical machine learning to characterize our quantum sensors. And now we can learn from how it behaves, and then we can model that. And on board, we can use it as a backup. So you see here, you just use a quantum sensor that is not perfect with just some machine learning, and we have a huge already advantage because now we don't need to synchronize it all the time from seconds like we do now to minutes. But Quanture, what is the difference? We want to be the brain over all those quantum resources to orchestrating all those different products. So for this accomplishment, we have already some papers that are related to the CARE idea, like the ingredients, scientific paper published, but the CARE or this layer was only disclosed in the technical reports. So we also conceptualized the integration management, how to do this, and also a first prototype, as I mentioned. For a roadmap, like I will be here very quick about it, but in essence is this transition, of course, is dependent on the evolution of this quantum technology. So you can imagine from having a quantum computer that is fully, error Theranos near intermediate scale quantum computer to be on board now of this airplane, let's say, example, and also evolving to a fault quantum tolerant quantum computer on board. So it's miniaturized. So, and the quantum sensors, of course, within those training, we have a feedback loop to make them even better and architecting and producing them in a better way from this interaction and iteration. So this iteration also have an effect on the hardware itself through our platform. So this is a really nice diffusion-assisted AI model that is here illustrating what could be, what is like a product that is embedding the hardware and the package of the hardware and the software. And here on the right, you can see maybe on a drone that someone said that their dream drone is to use these lithium niobate ring resonators as this fault-tolerant quantum computer on board in the far future. So what we are looking for is business angels and board of advisors in quantum computing. So we want funds for long-term 10 years and networking especially. So our team is me, Walid Shaifi. I have experience in quantum optics, master's from Sorbonne University in Paris, and PhD in quantum optics at Stockholm University, working on non-Hermitian topological photonics and single photon for quantum communication. And we have Anis, is already an entrepreneur in neurotechnology and specialized in hyperbolic machine learning. Thank you very much.
Thank you very much. Impressive results. Okay, and now the main part, questions from the jury. Yeah, who will start? Who wants to start? Tadas Paulauskas is keeping the mic. Yeah.
Well, thank you so much for nice talk, nice presentation. This is obviously a highly sophisticated approach, and it's probably for typical quantitons, it's probably even too advanced. But in any case, this is really, you showed a way forward that we can really imagine where putting all these things together, how they may merge and deliver something beyond that we now use. So most of this, your presentation, technical things were a lot of theory, right? How about more of some validations in terms of modeling, how it compares, how well you can achieve using these various quantum sensors, machine learning in terms of the time frame, what yeah, thank you.
Yeah, thank you very much. Thank you for everyone here. It was an honor to participate with this hackathon. It's wonderful. So for your answer, maybe I will take it a bit as an analogy. So if you take the roadmap of IBM, it's saying like next year we'll have fault-tolerant quantum computer that we can still start work on it. And in 5 years, it will be commercialized or on the cloud. So it's really, of course, it's a transition is very dependent on that. But what we have today is certain quantum advantage in, or let's say utility to be more precise in certain areas. And in those variational quantum algorithm or those QAOA, so we want to have, of course, kind of advantage over the machine learning and leverage this quantum machine learning. But also it's proved the way that even if we are at the same level as classical machine learning, we want to prove that the time scale is not as it was before saying it's 100 years. It's still in this next years, even next month. And we can take an analogy also with the AI, like everyone was saying that it will take forever, but it was exponentially faster than anyone could expect. So why is that? Is the belief. So you have to believe that it's the way to take it. And when people and Synergized start to work on it, like we have now the EU projects pushing that, even NATO with the Diana projects or any other institution that is enriching this adoption will accelerate, of course, those numbers very quickly.
As I see, Karolis Tashis waits to ask the question.
I have a question. So, okay, I'm navigating, I'm using your system. So to understand correctly that I will need to have a quantum computer with me or access to a quantum computer somewhere remotely, yes?
So what we said is we expect to have many quantum resources. One of them, what we have today, is quantum computer. But this quantum computer, we only can have it as edge computing outside, right? So you don't need to have it on board, right? But you can just, for example, in the moment, just train your model in that quantum computer outside, take those from using the time series of your sensors and optimizing, take this model and embed it in your navigator system such that now it learned better how to use your resource, which is the quantum sensor or even the quantum network itself. So at the first step, you don't need that. And ideally, you would love to have the ideal quantum computer inside on board, such that you have a real-time correction. You don't need to train outside, but it's real time and it's very personalized, let's say, on your specific case and adaptive, maybe even in combat or something.
Okay, thank you.
Victoria Trimble.
Hello, thank you for the presentation. I do appreciate the visual aesthetics of this slide in particular, and also the fact that you presented competition and how you stand out already in your pitch. I would like to ask you to elaborate a little bit more on the business model, in particular, as you mentioned that you are seeking investments and long-term investments. I do understand the logic behind the business angels and their expertise and contacts, but just in your presentation, I missed the discussion of business per se. And if you speak about investments, are you considering yourself ready for venture capital, or these are more like grant investments, that kind of, money, not like risk capital, but more grants and subsidies? What is your idea?
Yes, actually, it's a bit pity because the number 8 slide just got slided. So, but yeah, I spoke about it. I put it in the slides, but it was jumped. So the business models that we thought of is like a software subscription to use this care package, right? Of course, there will be version and the dynamical version of them. So it depends on your need. And also we thought of a sensor partnering with those sensor companies and in a model of revenue shares. Like each time you buy a package of care and a quantum sensor embedded very well, so they can have a revenue share from it. Also, we can have a revenue share from it. And also, an additional feature is to access to this quantum network access that is, let's say, private quantum network access. So you can have like subscription to it, or and also we have, like we thought about pay as you optimize. For example, you have very specific need like going stealth mode. Then you need very, very heavy, maybe more more planning and heavy modeling. So it's a bit broad.
Okay, Professor Remigijus Paulavičius. Is it on?
So really thank you for very, very nice and detailed presentation. Just to clarify, similar what I asked before about originality, you showed that you started, even you already had first publication in 2020, and in total you had like 3 publications, I guess, yeah? So my question is, first part of the question, is it already something was proposed in these publications, or it's originally developed for this competition? And second, you already started, let's say, 6-7 years ago. So why now? What's the problem? Why you didn't start, let's say, startup or commercialize your solution earlier? What happened? Is it like financial aspect, or it was needed some technological algorithmic breakthrough? Thank you.
Yes, for your first question, this care idea was only developed during this hackathon. This combining the idea of quantum with the idea of this Hyper-Steiner minimization or optimization problem by Anis. So Anis has this machine learning background on the hyperbolic Steiner, and I worked more with the quantum computing and quantum sensing part, which is because I worked with actually doing my PhD with NV centers in Diamond and so on. So no, this is not published in the combination of it. So for the other, why the adoption or is slow, like even for Q control, they were founded 8 years ago. Only today they have results, and even though machine learning was way before, it's also the fact that it's not sometimes enough that you have these technologies. You have also that they have a threshold where you can have repeatability of result and scalability. So here we expecting to have a better scalability proof because of this commercial availability. So because they are commercially available, it's proving that now it's more scalable and they are outside of just research. And what was it more? You had more questions? Hello?
Second part was related to why now? I mean, for the commercialization, you just now proposing solution, yeah? So what's the main iOS issues to start it commercialize earlier, let's say like 2 years ago? So it was like algorithmic progress, or it was also, let's say, hardware progress which needed for your solution to work?
So you are speaking about the commercialization of the software. Of course, this software cannot work alone without the hardware. And those hardwares are only those last years that are trustable. But also those, for example, the fact, if I take this just example of training with quantum machine learning, it's only recently that you can have very good connection or link, for example, with IQM in Finland, where you can use the quantum computer remotely using those unified packages like Qiskit and other packages. And so those are contribution. Even NVIDIA, the fact that now they have actually a hardware that is linking a quantum computer to the supercalculator. And now that we have these hypercalculation clusters around even Europe. So we want to use this actually to have access to these HPC networks. So they are actually growing and they are appearing more and more. And so that's why I said you cannot just quantum jump from what we have, but it's dependent on the evolution.
Andrius Milinavičius.
Walid, thank you so much for the presentation.
Thank you very much.
I'm coming from the venture capital. We like numbers. Can you estimate how much of funding you would require to actually get into the first pilot?
I think sub 100K for the
100K.
first like total integration of testing, maybe even booking airplanes and like real full characterization of it. But for the software care, of course, here the starting point is very much lower. So maybe even simulated data or bot data, then it will be much lower, sub 30K.
Is the human cost also included? What would you require to add to your team?
To consolidate our team, of course, we want better financial and advisors and management, and also like a broader view from some quantum advisors that could, quantum scientists that can steer and contain a bit. And also we want to have a strong and solid network within Europe, for example, when it comes to HPC or usage of time slots for the quantum computers, and experience with the PNT system position and navigation and timing systems. And also you can think of from the ethical or authorization law side, because if you want to do experiences with jamming, you have to have authorization, for example.
Well, or you can have very friendly neighbors, so we don't have this problem in Lithuania. And it sounds like more 500,000 is required for the stable pilot, right?
Yes, we can say that.
Okay, thank you.
Okay, I think the jury is satisfied with the answers. We can move on. Let's thank for Quanture. Thank you so much.
Thank you very much. Thanks a lot.
Okay, the last virtual group is Birantum, joining virtually from University Paris-Saclay, French, presenting Smart Grid, solving the energy trilemma.
Hello.
Hi.
Can you hear me?
Yes.
Okay.
Yes.
Let me share my screen. Can you hear my? Can you see my screen?
Yes, you can start.
All right. So I'm ready. All right. So hi. To begin, let's imagine a problem about energy response demand in 24-hour of a home energy environment with a step every 15 minutes. There are 3 controllable appliances: EV charger, washing machine, and dishwasher. And each has its own problem space with a unique constraints. For example, EV charger requires a 4-hour block, but it can only run overnight. Washing machine, 1-hour block, but only run during the day. And lastly, dishwasher, a 4-hour and half block, and it can run only in the evening or early in the morning. And these appliances create the massive search space up to power 101 possibilities. Additionally, when we look into the input data, as presented in your right-hand side, the baseline load on the top, and then we have energy price, and then the free renewable energy. We figure out that the renewable energy is not always available when the demand is high. And that is a typical problem. We want to compensate it as much as possible with a clean energy to reduce the peak load. Today's grid faces with a perfect storm. Volatile prices punish the customers. The peak demand threatens blackout, and the clean solar and wind powers are wasted daily. And this trilemma demands a smarter solution than a simple cost shifting. Hi, my name is Ben. I'm a team leader of the team Birantum. And today I'm here to share our solution to deal with the energy trilemma using the quantum optimization and quantum annealing. Our plan is straightforward. It's to use the new power quantum optimization to solve a set of compilation of the 3 critical problems for the energy grid. First, we minimize the total cost of electricity. Second, we stabilize the grid to prevent blackouts. Third, we guarantee that the service we rely on is always delivered. We do this not with more power plants, but with smarter software. Since I'm a physicist, I want to start from mathematical formulation. We translated this complex trilemma into the single smart objective functions. And think of it as a sophisticated balancing act with 3 diodes that we can control. The first one, the first diode minimizes your electricity cost. The second stabilizes the grid by shaving peaks. The third acts as a warranty, ensure that every appliance runs exactly once. And by turning these dials, our hyperparameter A, B, and C, we find that the perfect balance for the grid needs, delivering the lowest energy and the optimal outcome. But what is the difference between our approach and the Reddy chart that I mentioned above? In the Reddy algorithm, the peak term is completely removed, and it means that we solve the three independent problems instead of one connected system. All right, and with using Kubo and Anuner, we're able to take into account the entire search space with more than 2,300 interactions within the system. And it takes only 306 seconds to find the best solution in our local machines. And the results is presented in the left-hand side. To better increase the visibility of our results, we present it into a table below. With our Kubo, we obtain $55.57 with a peak load of 3.18 kilowatts. We obtain a cheaper total cost for the Reddy method, but it created a massive surge. Indeed, the great disaster. Especially with our Kubo, we obtain 73% of the peak reduction. All right, and let's talk about the three massive pressure gripping the energy sector today. For utilities companies, it is the financial hemorrhage, billions spent on temporary peaker plants and focused grid upgrades, all while facing the heavy penalties or unreliability. For the smart home providers, it is the value crisis. Their hardware is seen as convenient and not necessarily, making it hard to justify the cost and return the customers. And lastly, for the grid operators, it is an essential threat. The unexpected nature of renewable is creating a dangerous instability, risking blackouts and making the frequency regulation a nightmare. And these companies are DEF, Power, Cybergrid, E.ON, Google, and Amazon, and so on. We offer for the utility companies a predictable and dispatchable peak shaving resource. Our formulation guarantees the performance and making us more reliable than competitors. For the smart home providers, we offer a virtual power plant platform that can be turned for the multiple grid devices by adjusting the hyperparameters. And lastly, for the grid operators, we offer a white label energy cost optimizer service that turns their devices into money-saving assets and increasing the customer retention and product value. Our market is very big. In 2025, the market size was estimated $1.67 billion in Europe by Business Research Insights, and 55.2 billion in the world for diamond response market by the Future Market Insights Inc. Our business model is simple and scalable B2B API. We both license our great award Cubo for emulation as a backend quantum brain. Our customer may already spend millions of dollars acquiring user for their smart home apps, and the problem is that their current schedules are dumped and ready. So we would like to provide the intermediate and high performance upgrade that solves the peak load crisis and turning the existing products have the state-of-the-art rate management tools. For now, we have moved forward to the theory to validated proof. At TRL4, our model has already demonstrated a 73% reduction in the peak demand using the real-world data. Our path is forward to clear and lean to reach TRL6 is a working type prototype in the test home, and we will do two things. First, we try to connect to live utility data. Second, we command the real smart plugs in a control demonstration. And this technical depth is matched by our team. One co-founder is the architect behind our core quantum hybrid model. The other is validator who engineer the test proving is quantum optimal solution. And now we have the proven model, the executable plan, and the right team to deliver the commercial success. To put it simple, the greedy solution is a problem, and our great award optimization is the answer. And this isn't just a theory. We have experimental proof that our solution is 73% more effective at stabilizing the grid. We have the model, we have a validation, we have a team, and now we are seeking the funding, strategic partnerships to complete our transition from the lab to the real one. And this investment will fund our path to operational prototype and our first commercial pilot program. And thank you for your attention.
Okay, thank you once again. Okay, Andres already wants to ask a question. Let's
Ben,
start.
thank you so much. What is that investment you're seeking?
The investment, we are looking for some funding in order to pay the employers and also pay the running time on the real hardware.
Can you define the word sum?
Yes. For example, what specifically, right? That is your question?
Yeah, what would be the number you're seeking?
A number, because our code already successfully run on our local machine using the D-Wave system. So today D-Wave run very well. So if we hope that we can run on the real hardware, and for the hour in a real hardware is about 5,000 euros. And also this money we would like to pay our employers. That is one co-founder and one validation engineer.
Mm-hmm. Okay, also, can you help me navigate your ambition? I want to be a slight devil's advocate. It seems to me that for this problem to be solved, it's enough to have machine learning algorithm that would do exactly the same, cheap. How could you comment this? And what would be your ambition, your team's ambition in the future?
Okay. That is very clear. Machine learning model using the classical supercalculator all right, or classical computer, which only able to find the local optimization. And the local the local point, the local energy is not correspond to the global one. So using the quantum optimization, we can obtain the global optimization energy. So that is the point.
Okay, Co-Invest Capital, Victoria.
Thank you for the presentation. I will slightly join Andrews in being not a kind of business angel, but a bit of business demon, if you want. I just would like to ask you to elaborate more about your assumptions and actual calculations, because I would kind of challenge your first slide where you were speaking really from retail consumer's perspective at home, and probably that's why, you know, Andrews is saying, is the price of a solution justifying the problem? And I will also question whether the washing machines and dishwasher machines are being used during daytime, because majority of the tech right now allows you to postpone and use, you know, the cheap off-peak energy. But, you know, so like this slide is about maybe a problem of a single consumer, but you are talking about the grid and the grid load. So what kind of other data points you were using, you were analyzing, you know, because on like overall electricity grid, I would assume the actual usage is coming from completely other user segments.
That's a great question.
I'm sorry, it's really hard to hear. Can you repeat in slowly and shorter and louder, please? I'm sorry about the internet.
Can you hear me now?
Yes, I can hear you. Yes.
When you made your calculations, were you using only consumer data or other data, which probably is a bigger users of the grid, you know, load?
Yes. It was single user, yes, or like bigger one? Mm-hmm.
Yeah, for a single user, yeah. Yes, so for the single user that is provided by with the hackathon project. So we use the provided data to provided input data for a home, so for an user.
For entire home, yes? One user. Okay. Remigijus Paulavičius.
Okay, thank you. So first, very little question I will ask you to clarify later when I will stop my questions. So what you meant by saying our local D-Wave machine? Do you have like already D-Wave running on your home institute?
I see. Okay, my local machine is my laptop, because we can solve the problem using our laptop already. So for the scannable problem, we hope to use a real hardware for the bigger problem, more complex problem.
But what you mean your laptop? You're running D-Wave, so you cannot run like proper D-Wave, just simulator, yeah? But if you want to run like proper annealer, you need to use, let's say, D-Wave through clouds, yeah?
No, that is how to say, emulator.
Yeah.
Emulator and...
Yeah, but it's not real quantum hardware, it's emulator.
Yes, but for example, D-Wave machine annulers will run typically not the same way, but it's more powerful with there are no error. But for this very small problem, first of all, we do not have the running time. So for running on a D-Wave problem, I think it can run smoothly because there are no error. And there one thing is more powerful, but we need to spend a lot of time to be in queue.
Yeah, I know the situation. I also running sometimes vSoft hardware. So my question then is the following. You showed comparison like your, let's say, local D-Wave emulator results against greedy algorithms, and you showed that you received a pretty good performance increase. I'm just curious, is it like greedy, like the best classical algorithm for your problem? So you did like proper benchmark, selecting the best algorithm from the classical world. There are really many different classes to solve this problem, yeah? Heuristically.
Yes.
Not deterministically, yeah? There are different ways. So is it like really best classical solution which you were managed to obtain? In
Yes,
the next
because
slide, not here, not here.
This one?
No, where you compared the results in the table.
Ah, here.
Yeah, here.
Okay, so what we did, we because we play with the hyperparameters, okay, and we do not sure that if we set a random hyperparameter, we will obtain the results, the global minimal energy. So what we did, we run with a grid 3 times 3 times 3 of there are like 27 set of parameters, and we in the end we obtain the lowest energy for only one point, and we try to apply uses the same ABC parameter for the gradient chart. So we pretty sure that we find the lowest energy with this set of parameters.
Okay, I'm not that sure. And when you say that it's like optimal solution, are you sure it's optimal or not suboptimal? It's like a heuristic strategy. How you can be sure that it's really optimal, global optimal? Because you stated that it's like optimal solution. You see here. No, in that slide, you're stating that it's optimal solution.
I see your point. I see the point, but yes, we need to check on the D-Wave hardware as well too, to check if that is really the global optimal. You are absolutely right.
Okay, thank you.
Is often like that. Karolis Stashys.
Okay, I have a much simpler question. So, okay, you mentioned that your solution might help the end user save money, yes?
Yes, end user, yeah.
Okay, so let me tell you an example how we do in Lithuania and the Baltic states. There is online website where we can check the next day hourly cost of electricity. So if I see that at a certain hour there will be an increase in price, I just don't use electricity at that time. And almost everyone uses this method to save money and to reduce grid load. So how is your advanced algorithm better than the current one when we just check the prices and don't use electricity at that time?
I cannot hear you well. Sorry. Can you repeat shortly and louder?
Okay, do you hear me now? Hello?
Yes?
Yes, you hear me, yes?
Yes, but sometimes it interrupt. Yes, please say slowly and.
Okay, thank you. I see that there are some issues.
Yes, I have one question. So for me, this, I'm not an expert, but for me, this seems like an machine learning problem. I mean, do you really need quantum calculations to optimize?
Okay, so that is more like quantum machine learning, and for today we can use its own way in the lab for quantum machine learning. We hope that in the future it hasn't proved that there are advantages on quantum machine learning. We hope that in the future we can use quantum optimization to find the global minimum. But today, I think today we can use it using the neutral atom hardware and the photonic hardware, which are more suitable for the quantum machine learning. But the problem today is they have only few qubits on the neutral and photonic hardware. And it depends on the problem. If the problem is small, for example, it needs around like 100 qubits, I think it runs very well using the quantum optimizer to find the lowest point.
Okay, thank you so much. I think it's a lot of questions and a nice discussion. Let's thank for Birantium team. Yeah, thank you.
Thank you.
Thank you so much.
Thank you. I'm sorry for the internet.
Everything is okay, virtual world. So now, Umbrella team, and someone told me that Vilnius University Faculty of Mathematics and Informatics is not on site, but virtually. Is it true? Team Umbrella.
Yes, hello everyone, we are online.
Yeah, you are far away from Soletica. Okay, so their topic, predicting drug toxicity with quantum machine learning. So, Edward, please.
Yes, hello everyone. So we basically tackled this problem, which is very relevant to pharmaceutical industry. So our main problem is, the main problem, not ours, pharmaceutical industry, is that there are very big costs for preclinical trials per every drug. So if you want to test new drug, it will, on average, can cost up to $100,000. The testing phase lasts 24 weeks, and after that, only 10% of the tested drugs go into the next phase. So, and we offer a solution.
So, what could be our solution? So what if we propose a tool which could avoid clinical trial expenses for already doomed candidates? So what if you make an algorithm which takes already extensive amount of data about drug toxicity, and it runs the potential candidates through this algorithm and classifies whether it is toxic or not. So by doing that, we could avoid unnecessary testing on the doomed candidates, and we would save lots of money and weeks of research time, and use that those resources for the successful candidates. So that would be our proposed solution.
Our unique selling proposition is that basically we combine advantages of machine learning algorithms and advantages of quantum computers, and especially keeping in mind that quantum computers are getting even better and better by months, by years. They are very good for us, and we have good brains, we have fresh brains, and we are ready to put in a lot of work if needed. So our product
leverages the quantum computation power. So first thing that it does, it processes the huge amount of data that we have. It chooses the best features and samples the data and scales it. It then moves to the machine learning algorithm, which we chose to be support vector machines. As during our research, we saw that it works the best with quantum kernel approach. As for quantum kernels, we also tried a few different approaches, which were basis, angle, and ZZ feature maps, and all of them showed quite differing results. And this algorithm we tested on Vilnius University's hypercomputer, which allowed us to test with bigger datasets and higher amounts of qubits.
Yeah, so basically we didn't find yet very good and very accurate algorithms. However, we reached 70% accuracy rate and ROC AUC 77%. with Angular X encoding and with few other similar encodings. However, these simulations on current hypercomputer took a lot of time. So each simulation can run between 2 and 5 or 6 hours. And yeah, how we can improve these results already by doing more smarter sampling, such as cluster convenience or quota sampling. We can do more qubits and test with more samples. That would take a lot more time of a hypercomputer. However, if we tested that on real quantum computers, it would take less time. And probably it would yield better results with bearable computational time.
And now to pretty much wrap it up, this is our team. This is us. We're all from Vilnius University's Faculty of Mathematics and Informatics. And we are all in different stages of our education. So we have 2 people studying for their bachelor's degrees, 1 master's student, and 1 PhD student. So we all we have a range from new innovation and fresh minds and some experience in the field. So there's also our contacts. If you are interested, you can write to us. And with this, we would conclude our presentation. Hopefully, you see the value of this product. And if you have any questions, we will do our best to answer them. So thank you.
Okay, thank you, Umbrella. Thank you, Agne, for summarizing everything. Who will start with questioning? Tadas Paulauskas. Yeah.
Thank you, Team Umbrella. That's a nice comparative study. Looks like you've put a lot of work in this. Could you comment on in real applications what kind of data would you typically need for drug toxicity, or how the quality of the data impacts that? Thank you.
So about type of data, it basically needs, I do not remember from out of my head, but it needs every information possible about certain components, certain drug. So, and about the quality of the data. So why this algorithm is pretty good is that we already reached almost 70% accuracy and 77% accuracy with only 500 samples. So we trained data on 500 samples, and that's comparably very low amount. So most data sets contains thousands of samples. So we can easily reject samples which are not qualitative, or if they miss some features or something, and we can choose the best features to train better data. Yeah.
This wanted first, or Victoria goes? Victoria Trimble.
Okay. Thank you for presentation. I have to say that when you have drugs, you have those little, long pages with a small print. So your small print on one of the slides genuinely made my day. So thank you for that. And the question would be, if you could elaborate a little bit on your business model, the kind of probably optimistic thing would be that your estimate of the standard costs of 100K in our assessment as investors is probably 10 times lower than the actual cost, if not more. But how would you see your business going forward? Whom you would be charging, how you would be selling, what might be the price of your solution? Or if these are questions too early, that's also perfectly fine, but I would just like to hear your thinking.
So thank you for the question. We didn't give a lot of thought for this. However, our basic understanding of this model would be, first of all, to improve our model and to be sure that we can train model on different data and train it pretty accurately. Second step would be talking with pharmaceutical companies and trying to understand what data they have, what are their needs, what are their biggest pain points, and how we can overlap and sell them this model based on subscription. And yeah, our model, what it would do, it would filter the drugs which have the highest probability of being toxic, and some of those drugs may not go into clinical pre-trials and save hundreds of thousands of dollars, basically. Yeah. So I don't think it would be very hard to sell, but it would be the biggest problem right now is to improve our model accuracy, but it's doable. I hope I answered the question.
Okay. Okay, Karolis Stashys.
Can you, Carlos, a fast one?
Okay, Andrew.
Could you guys also elaborate slightly, as same question as the previous team, how much money to do a good, stable pilot?
Okay, be practical.
That's a really complicated question, but
Okay,
what we basically...
1 million. Can you do it with 1 million euros?
I believe so.
Can you do it with 100,000 euros?
We basically would need most money for contacts, for attending various conferences to get for networking and for quantum computers. We didn't look at the prices, concrete prices, but
you should go on
we can do it for
Innovatio Agentura website. There's a lot of funding for these kind of things available today.
Okay, keep in mind that. Karolis Stashys? Yeah?
Okay, so hi. What I was missing in your presentation was that you did not present competitor analysis. And you see here in Vilnius, only in Vilnius, there are at least 2 startup companies which are fully operational who are already using artificial intelligence for new drug discoveries. So that's one thing. You didn't check the market. Another thing is, this is a quantathon, quantum hackathon, and you put the most emphasis on the artificial intelligence. In your case, you showed a good problem of the clinical trials. But in your case, you are trying to solve not only the clinical trials problem, because there is a huge amount of companies who are doing that, but you should have focused more on how long they are working on that, how much resources they are putting on artificial intelligence. And your presentation would have been perfect if you just showed, here is our algorithm working on simple computers. It takes, for example, 10 hours to check one drug. And here is using our quantum computer algorithms. It only uses, for example, 1 hour. And that is increase or decrease of 90% of power consumption, time consumption, everything. That would have been perfect. So that is more not like a question, but a remark for the future.
Okay, future
Thank you.
remark received. Mantas Šimėnas. No questions? Jury is satisfied. We should move on. So on site, now we are preparing our computer. Yes, because next team is here. Next team is not today Eve, but we will present today. So, Vilnius University, Faculty of Physics, Quantum Link Anywhere. Okay, Gediminas Usevičius is going to start his presentation. Okay, some technical issues.
Yeah, it's a little lag.
Okay, for our technical support, yeah. It's like when the naming of team.
Giving a breather for jury. Sebastian. Okay.
Okay, sometimes it's really easy. Thank you. Yeah.
Okay, hello everyone. Let me thank organizers and the jury for the opportunity to present today in this hackathon. We are not today Eve, and we are from Faculty of Physics from Vilnius University, and I am Gediminas Sisavičius, and today I will show you how we can establish a quantum secure communication anywhere, quickly, reliably, and independently of established infrastructure. We call it Quantum Link Anywhere, deployable quantum communication system for the field. So as you already heard, classical communication is no longer truly secure. Radio and satellite links can be jammed, fiber networks can be tapped, and as quantum computers continue to advance, today's encryptions will eventually fail. That means that in times of crisis and conflict, communications can be intercepted or disrupted, exactly when they are the most needed. So, what we are proposing as a solution is a modular, mobile, and fast-to-deploy quantum link anywhere, which allows us to establish a quantum communication channels on demand without relying on any pre-existing infrastructure. It's a system designed to bring quantum security wherever it's needed. And here's how it works. Let's say we want to establish a quantum communication channel between two bases 50 kilometers apart. We will be using drones inspired by novel innovations and employment in Ukraine. The said drone will be guided using an optical fiber, and it will reach the other base. Then the optical fiber will be disconnected and connected to the base, thus establishing a secure quantum channel. Through this fiber, a quantum key then can be distributed securely, and the speed of such deployment only depends on our drone's speed, which is typically 7 to 8 kilometers per hour easily, meaning that such a quantum link could be established in only 40 minutes or less. But let's say we want a quantum communication link which is farther apart than just 50 kilometers. Well, then we cannot just use optical fibers, because as the distance increases, the losses starts to dominate, and we need something new. What we are proposing is a quantum repeater unit loaded into a vehicle or truck. Quantum repeater's main purpose is acts as an extension of the optical fiber, allowing the signal to travel for longer without actually any losses taking effect. In this case, we would launch multiple drones from bases that will fly to the quantum repeater unit, and once they are there, the fibers will be disconnected and connected to the repeater, thus establishing a continuous secure quantum communication line. So in principle, how this works is drones lay the optical fiber, and the quantum repeaters extends the quantum communication line, allowing a continuous secure quantum link. And we don't have to stop with just 100 kilometers, one repeater. We can actually extend this quite further. Once we have established one quantum repeater, adding multiple of them to actually extend our quantum channel is as easy as doing it for once. And for example, if we would like to make a quantum channel, quantum communication link from here, Vilnius, to the coast of Lithuania and Klaipėda, it would take only 4 hours. Of course, this could be faster if we ignore the driving speed limits, but I digress. So advantages of this, our technique is we are turning secure communication from the fixed infrastructure into deployable capability. It has all of advantages of secure quantum communications. Its rapid deployment anywhere in the field within hours makes it invaluable in the military and national security aspect. Also, since we are using optical fibers for the quantum communication itself and for drone control, it's immune to radio frequency interference and jamming. And what's actually the most amazing is that all the technology needed to achieve this already exists today in the lab or the field. All the subsystems like quantum repeaters, their memory, optics, detectors, they already have been proven to work. So when it comes to what's already today, when it comes to quantum communication, the main ones are secure network relying on trusted relays in Vienna, as well as the Beijing-Shanghai backbone, which spans a vast 2,000 kilometers in China. But their main limitation is they are stationary, they rely on trusted relays, which must be physically built and physically secured. So they are, one second. So they are taking a loss in security, but to achieve what we are proposing today. Also, one of the newest developments are satellite quantum key distributions like Mitzius, which have intercontinental range, but they are very expensive and they are not very reliable as they depend on weather conditions. Applications of our technique, apart from immediate use in military and national security, are with additional development, we can use quantum synchronization networks enabling GPS-independent timing and relative positioning. Also, its scalability allows us as a backbone for future quantum internet infrastructure. As I showed a basic link from here, Vilnius to Klaipėda, it can be, with additional development, can be extended throughout the whole country and neighboring regions. So our development plan to achieve this begins with a laboratory prototype, which then will be mounted and secured into a vehicle or a mobile truck. Then we will be performing field testing to see if we achieve the desired results. And once we've done that, we will scale it to see if we can go across multiple mobile nodes. So, in short, Quantum Link Anywhere establishes quantum secure communication channels on demand using mobile quantum repeaters and drone deployed fibers. Operates independently of any fixed and already existing infrastructure or satellites. It combines the proven already existing technologies into one single field-ready platform. And it has potential to lay the foundation for future quantum networks in communications and navigations. So we are Quantum Link Anywhere, and we, as a Not Today Eve, present our work, and I hope you have many good questions. Thank you very much.
Thank you. Nice.
If I may start.
Yes, please.
So what did you achieve during the hackathon?
So what we proposed and what we researched is how we can combine all those existing technologies into one mobile unit that would actually work in the field. Though this right now is just, let's say, a concept with many proven research and testing, it's still not here. We haven't done it. So our goal right now and plan after this hackathon is actually to see how far we as a team can push this into reality. Sorry. Yes.
Thank you for the presentation. I would also like to ask you to elaborate a little bit on what is exactly your solution. And correct me if I'm wrong, but I kind of understood that basically you're proposing to organize the process, the logistics, if that's my right understanding, or you are developing the quantum repeater or doing something else. And then just, like a very practical question in your picture of this quantum link, and especially as you are using, some military examples, what would happen if one of those trucks would run over a mine or just, somebody will launch missile, and that truck is gone.
Thank you for the
And the
question.
missiles are coming in quantities.
So it was a long question, so if I forget, please remind me again. So what we are actually proposing, so right now, all of the quantum communication infrastructure is mainly focused on building stationary infrastructures that can be used as a backbone for future quantum networking. What we are proposing is, in the need of emerging demand, how we can establish a quantum link between any two or more bases or points of interest. Because no one is actually, at least openly, not working on this right now. When it comes to what happens if one of our components units gets damaged, so if the drone gets damaged, it's quite cheap to replace and send another drone to establish the actual link. If the quantum repeater unit gets damaged, it becomes more expensive, but again, it's a mobile unit. It can be just sent a new one to establish and connect to actually the needed location.
Or arrange the drones.
Is that everything? Maybe. Okay.
Carlos Tashis raised a hand, yeah? Or aha, he needs the mic.
Okay, I have a question. I'm quite new, unfamiliar with quantum repeaters. Please fix me if I'm wrong. So, when a quantum key is traveling and it reaches the quantum repeater, I think it is somehow interferes the quantum repeater with the quantum key. It's just like intercepting it, yes?
So actually, that's one of the advantages of the quantum repeater in what, for example, China is using in their backbone, is that quantum repeater actually never reads the information it gets. What is happening, if we want to go technical for a minute, it's actually performing a Bell state measurement that actually swaps the entanglement of our quantum key and then is able to, let's say, regenerate that key to travel further as it was just sent from our base or our generator source.
So it's not impossible, for example, in the quantum repeater car, to get the key without other part knowing it?
No, it's impossible. Quantum repeater itself doesn't actually read the information or quantum key. Its main, its base is actually on quantum memory, which stores the quantum key, which is in the process as a BSM measurement is made.
So are those quantum repeaters available on the market now?
So they have been tested in the laboratory. The main challenge with them is actually the quantum memory. But me and my team, and also recent developments, we already have a prototype as a calcium tungstenate doped with ytterbium ions, which shows great potential to be working could be working the working quantum repeater prototype.
So you build it as a product, actually.
So
it could be your product.
Yes, we will definitely see if we can do it right now, or we will have to, for example, collaborate with other labs that are more proficient in this field. But it's definitely an idea we are thinking to achieve.
Okay, thank you.
Tadas Paulauskas.
Thank you, Gediminas. That's first of all, very nice pitch. Some kind of, I was expecting someone who's gonna, give a nice pitch. Eventually, like a high energy pitch.
Thank you.
So the solution, I think it's really creative and kind of targets a real need to have mobile, deployable, etc. So I think that's nice creative approach. I think generally some of the things maybe you already consider, and that's right for the future. For example, laying the fibers on the ground that, first of all, people, seen that even they can use QKD networks to use as seismographs. So if there's something, train somewhere nearby, it impacts the, qubit rates, errors, etc. So laying things on the ground, that's one of the things how, maybe you have some idea how to, work in the future with that.
So it's a real challenge that is actually very difficult to overcome for a long term. But as an idea for quantum link presented in this moment is mainly to focus how to quickly establish a link. It's not for like years, 10 years. We need a quick way to securely communicate. So that was the main focus. We have been thinking about how we can combat that, but we have not come to a real solution that we can actually present today.
Okay, any more questions? Remigijus Paulavičius.
Hi, really good pitch. So my question can be a bit silly or a bit stupid, but that's the way how we do progress in technologies, by asking this kind of questions. So you showed prototype, yeah? Initially, I understand that's your main, let's say, advantage, innovation is on the concept, but now I also understand that you need some progress technological for these, let's say, also technological elements which you are using in your concept. And what if I will change this truck or car by another drone? Can you do this completely drone solution?
It's a bit difficult with the current technologies because the quantum receiver itself, as today's technologies would allow, it will take some space. So that's why we decided to use a truck, a vehicle, where that thing could fit, because it will need quantum compressors, quantum memories, and other components to actually achieve what we want. So no, drones cannot be used at this stage with the current technology. Though we have a plan how we can, let's say, take a hit in a bit of security and go with, for example, trusted relays to actually achieve the same results with, for example, trusted relays. Because the main idea was the concept. That's how it started. And then we thought what we can use, what's available to actually achieve it. So we can actually take a hit on security and use, for example, trusted relays to maybe then use a drone approach.
Thank you. So, any more questions? I think nice idea, and we heard that even quantum memory, which is part of this idea, is developed in their laboratory. So,
thank you very much.
So it was clarified. Thank you. Okay. The last but not least, yes, so quantum beacon or bacon, they will tell us how to read this yes, or pronounce it, the team. Quantum Bacon is representing the Center for Physical Sciences and Technology, Lithuania, and where work or challenge is Quantum Navigation Challenge. Yeah, so 3 members of the team.
Presentation iš karto.
Once again, technical issue.
Full screen turi padaryti, ja?
Okay.
It works.
Okay, we see the slides. Yeah.
Just move. Yeah, okay. Okay, hello everyone. Thank you for already for nice presentations before. Just to reiterate, we are called Quantum Beacon because we have 2 dots on the A, and that's for simplification of word beacon for, of course, some navigation thing. But bacon is also very funny and delicious. So, okay. So let me start. Okay, so I would like you to imagine the world without GPS.
Of course, if we already take into account the presentations that were already done, we can quite easily imagine that situation. But from a more comedical perspective, let's say you are traveling in another country and suddenly your GPS goes down and you can no longer find a hotel. What do you do now? It's a very difficult situation. Of course, not something that will be too problematic in a worldwide thing. But for example, in security terms, or even as an example, let's say a plane flying somewhere else and then it loses accidentally its navigation data. It can be catastrophic. So it is quite a huge challenge to solve, of course. And the main reason why GPS fails in principle is because GPS signals are quite weak. We're dealing with a satellite that is above our atmosphere, and we have a very weak signal. And of course, what we heard already before, everything can be jammed, so it's not very nice. Also, another thing is when we have GPS, also we're usually also sending out some data because we want to receive where we are afterwards. This sending data also gives us another problem, which is that we are now detectable. In the military scenario, this is very bad because our enemy can decrypt, for example, our information and then know where we are at that point and, let's say, throw a bomb on it and it's over. So what we were planning to do is propose a solution that follows visual odometry. Visual odometry, as a principle, analyzes a set of images, and then we track in those images some prominent objects, let's say buildings, statues, something that can be extracted as a real thing. And we reference it with the magnetic field of the Earth, which is the North Pole. That way, we can, in principle, triangulate our location with any object on land, completely disregarding any radio communication at all. Now, to show you that this is, in fact, a working thing, I did some very bad calculations in principle and took some triangulation of, for example, if I move from, if you can see my mouse, yes. If I move from, for example, Life Center by having physics faculty and Life Center and this apartment building as a triangulation object, move to this location. And with very quite bad accuracy, one degree is quite bad in principle, I managed to obtain a 20 meter deviation from the real location, which can actually appear on very cloudy days, for example, even with GPS. So it is quite nice. Due to this, we can then plan how can we modify it and how can we use it for real. And of course, exclude the human factor as well afterwards. So I will give it to my colleague for this.
Okay, so for our device, we use a quantum NV magnetometer, which of course makes our resolution for finding the north a lot higher than 1%. We, of course, use an inertial navigation system just for understanding how much we actually walk in a short distance. Camera just, we could use any kind of camera. Today's cameras have good resolution, and of course we use machine learning for now, and we added quantum, but it's not really that necessary. So for the market size, the total addressable market size for non-GPS devices in military was 11 billion USD. This could be kind of sliced up to space and marine and ground-based, which we are trying to cut our niche is 5 billion. And we are thinking about getting 2 billion market, trying to fit into the 2 billion market, which is the tactical grade market. So why you should buy our device? There's no pre-mapping. That means we don't really need to know the place or update the maps. We just know where we were, and we can capture the photos and know where we are going. It's really customizable, which every part could be replaced, which kind of is really good. As my colleague said, detection and jammability are really bad parts, so our device is both undetectable and unjammable. And the best part is the infrastructure is already here with like magnetometers, not even NV, already in the market. And the only thing we would need is the AI to help us with finding the solution.
So, as we already discussed, our product is actually relevant to many, including the military, the governments, an average civilian consumer, and even maybe the academy. But our primary focus is going to be on the military, as the stakes of GPS jamming is kind of the highest in this sector. So naturally, it's going to be the most relevant for them, especially because our result is a product that is really simple, so it can be fixed by almost anybody. And if it so happens that it just breaks to an infixable extent, it is really cheap to replace compared to the other solutions that are being developed right now. And as for our plan to this result, we can separate it into 2 stages even. And during the first stage, we could develop a software that could be already released into the market for the users to download and integrate into their own devices, like, for example, their phones. And in the second stage, we could build and commercialize our own standalone device with the software already integrated in it. And to do this, we have a motivated and an interdisciplinary team of members who specialize in machine learning, in material science, light engineering, and even chemical physics. But this is where I want to bring my attention to you, because to develop our product further and for our product to develop successfully, we need to extend our expertise. So we are looking for advanced and experienced programmers and machine learning specialists to join our team, and of course, software developers in the later stages to give our framework a more of a shape. Because we believe that here we propose a realistic solution for a ground-based GPS replacement system. So I hope that we have piqued your interest, and I thank you for listening. We'll take any questions that you have.
Okay, so who is going to start? Any questions?
Again, why no one is speaking about the money?
Money.
Do you need money? You need people, you don't need money.
For now, we need people, but if we imagine that we have the people, almost all of the money that we need is going towards those people, because all of these technologies are kind of developed already. We don't need a lot of investment into them. So
can you estimate how much would you require for 12 months of stable operations?
I have approximate estimated, for example, if we take right now, if we are five people team, and we just do stage 1 for software development. So if we estimate, let's say, 1,000, 2,000 euros as salary expectations for each person for a full-time job in this situation, we will get about 10,000 something a month. So if we talk about a year, it goes about hundreds of thousands, so 100,000, something like that, minimum estimate.
Yeah, don't forget that there's social security.
Yes, of course,
yeah.
yes, of course.
So it's double.
Yes, of course.
Okay. Yes.
Nice. Okay. Any more? Karolis, Stashis, and after Mantas.
Okay. Since your system works on also using like other objects as a reference point, how it will work in a forest or on no man's land where everything is destroyed?
We have thought very well about this question, and thank you for the question. I have a few answers. Two situations in this case. We have a forest, very densely packed system, and we have a plains where there's very little objects in the system. So in the case when we don't have much objects, there's practically two options we can take. We can build our own temporary objects in the system and then track them because it's quite, let's say if it's quite flat and I can see, let's say my pole that I set up 3 kilometers away still, then it works. In case if I don't have that luxury and I cannot leave anything, I can still measure terrain. Because if I have a hill, let's say far away, there's like, let's say a hill, and then I move somewhere else, that hill approximately stays the same. So then I can triangulate based on the hill approximate location. And it's just one object. Now, if we have forest conditions, we can do another two solutions in this case. We can either take pictures a lot of times and then basically map the forest, or a simpler case is to take a drone, send it up and measure objects beyond the forest line. And we basically solved it in that case.
Okay, thank you.
Mantas Šimėnas.
Thanks. So I have a question. Do you really need NVs in this case? I mean, quantum sensors?
Quantum diamonds, yeah.
We can go away without it, but in principle, we want the biggest inaccuracy comes from the angle measurement. So if we have two objects, let's say, that are very far apart, and the angle between those two objects is pretty small, we want to, as accurate as possible, measure these angles. Now, we can already use a simple compass already. As I showed with a simple 1 degree accuracy compass, I can get a quite good result at short distances. But we can then imagine a situation when, for example, magnetic field doesn't work. Let's say if I'm slightly above the airline, let's say, and I cannot see the surface, then I can switch. I can switch to, let's say, anomaly mapping or something like that to completely change the system. So it's fully customizable. Even the camera itself doesn't have to be a camera as an image sensor. It can be something else, like a radar or something. So as one of our points, as customization is very good in this case.
It can be infrared, for example, if you want to use it at night as well.
Yeah.
Any more questions? It seems that everyone is satisfied, yeah? Aha, Tadas Paulauskas. Okay, so the last question.
To clarify the approach, right? Because this is very, once again, I think this is a creative approach. So it's because I'm trying myself, right, and I understand. So here you have a sort of some sort of local navigation combined with some external, like magnetic field that gives you some kind of global guidance, right?
Yes.
Plus, what do you else have? Like
basically, that's it.
Yeah.
That's all we need. So because magnetic field is already in the Earth's framework, we don't need to invent anything new in this case.
Okay.
So just
nature gives it.
Nature gives us the logistical framework.
Yeah.
That's cool. Nice. Thank you.
And nature plus physics gives incredible results. Yes, jury, already our discussions begin. So let's applause for our final round team. Yes. Thank you so much. So all presentations are complete. Now jury will step out for 10 minutes to discuss the results and decide who is the winner. Yes, and after that we will announce the winner. So 10 minutes. Okay, so.
I'm Karolis, so I was given the burden of announcing the winners. And so let's start. The third place goes, and with a group prize of 200 euros, we dedicate to AGKR Superposition from Latvia. Okay, so maybe a short word from our third place winners.
A nice one, yeah. Congratulations.
Okay, yes. Basically, thank you everybody, yes, for organizing such a great event. That actually was the first hackathon for us, Quantathon. So that was a great experience, and thank you, jury, for the third place, and we're looking forward to work together.
Thank you. Okay, now will be the silver place for the second place, and with the prize of 400 euros cash, and with the ability to negotiate with Baltic Sandbox Venture Funds of €500,000. To make their product solution come true, we dedicate it to Not Today Eve. Please join, come. So you get the heavy burden also to make your solution true. Next year, at the same time as now, we want to see the prototype in our hands. So will you do it? Yes. Okay, I like the enthusiasm. Okay, and now...
Can I say something on behalf of BSV Ventures? Congratulations. Yes, you need to understand that we are an early stage fund, right? So we are the first check usually. So you are invited to talk to us. We will discuss, we'll see what is happening. And if we're successful, you will be funded. Thank you very much. Okay, congratulations once again.
Okay, now is the moment of truth. Let's inhale, exhale. Everyone feels their hearts pounding. That's a very good feeling. Now, the prize for the first place is 600 euros in cash. A very good price. A lot of kebabs will be available for that. And capability to negotiate with Baltic Sandbox Ventures for up to €1 million grant investment. Okay, I got you. So this team, we have a lot of hopes on them because we found their solution closest to the market with the biggest impact to society and with the best capability to do it. And who will be that? After the ads. Okay. Let's congratulations for Quantum Beacon. Come, Quantum Beacon.
Please come to receive your prize.
It was a very hard decision to make. There were teams were very close, but we have a certain belief that you can actually do it a little bit better than others, but we have great expectation in you. Congratulations again. So, a little question for you for the last. Next year, this time, will it be? Okay, or maybe spring?
I don't know.
Okay, in summer. I will be checking you in summer. So you also not only you getting the prizes, but you will getting the eyes on you from FTMC management. You will be also discussed regarding internal funding. We have our great hopes. Thank you. Thank you, Quantum Bacon. Let's have some bacon on the evening. And I would like you to stay a little bit longer. Our jury has a special prize. 2 tickets to a conference in Latvia, Quantum Information Processing Conference. We established this prize thanks to our partners in Latvia, and we would like to present this prize to the team Umbrella. Umbrella, are you here?
We are here, we are very happy.
We believe that you will learn a lot in that conference. Our partners are waiting for you, they are already informed, so let's hope that next time you will increase your presentation, your work, and you will be the winners, because you were very close. Thank you. Yes, and a little comment from our sponsors.
Well, as a managing director of Coinvest Capital, I have to confess, you probably understood that the potential prize we decided not to award this day, but we are very, very grateful to all the organizers and all the teams that have participated, because for us it was the opportunity to see what is happening in the Lithuanian quantum ecosystem. And we will be looking forward towards your development. And I just want to let you know, if you are doing research and you are considering a spin-off of the scientific institution, our fund, which is state-sponsored, has a unique incentive for private co-investors. So if we would invest into startup, which is a spin-off from a university, our maximum return will be capped at 4%. And if we have successful exit, all the surplus will go to co-investors. So this is a great opportunity for scientific startups, and we wish you to develop further with all your research. And we are looking forward to see you next year and the year after, and after speaking and accelerating at our partners, BSV Ventures. So we hope to award our prize at some later stage. So congratulations and thanks to everyone.
The last word, okay. 1, 2, 3, and the last word from me, let's say. So thank you once again for participating in the Quantum Boost. You had a full month to solve the challenges and dive deeper a little bit into those subjects. And actually, we had quite a lot of teams, and not all teams were able to finish those challenges. I'm really glad that you guys actually showed your competence and, let's say, resilience and thick skin to tackle those challenges. And one last word from me, I would encourage you guys, do not stop, continue your journey, try to find better solutions, maybe a little bit better polished solutions, so our risk capital people will be more interested. Okay, so this is the last word. Okay, so thank you once again, and I will invite everyone to have a picture.
Okay, people from team smile. We can see you.